Picture yourself for a moment, standing beneath the night sky, your gaze captivated by millions of shimmering lights. While they may appear fixed in place, each one holds boundless chronicles of our universe's past and future. In this experience, you can sense a profound harmony, making the world feel simultaneously immense and within reach. Which leads us to ask, what exactly is the cosmos, and how did we begin to comprehend what lies beyond our own world? The cosmos is far more than a void. It's a colossal environment filled with gas, dust, magnetic fields, and radiation, populated by celestial bodies like planets, stars, asteroids, and galaxies. Within this boundless expanse, our own solar system represents merely an infinitesimal speck. It contains 8 planets that orbit the Sun, each one distinct and enigmatic in its own right, varying in size, composition, atmosphere, and orbital path. For instance, consider Mercury, a compact, rocky world experiencing drastic temperature swings, contrasted with Jupiter, a colossal gas giant boasting an exceptionally strong magnetic field and storms that can rage for centuries. Humanity's initial forays into cosmic study were entirely intellectual exercises, as people observed the stars and planets with the naked eye, attempting to decode the patterns of their movements. Early thinkers like Pythagoras and Aristotle theorized about the nature of these celestial objects, proposing that Earth was the center of everything. This geocentric view prevailed for many centuries, even as a few ideas hinted at our modern cosmic perspective. As scientific methods developed, however, observations of the heavens became increasingly precise, setting the stage for a revolution in thought. During the 16th century, Nicolaus Copernicus introduced his heliocentric model, which positioned the Sun at the center and had the planets revolving around it. This was a groundbreaking concept that became the cornerstone of modern astronomy, and it was further supported when Galileo Galilei used an early telescope to discover Jupiter's moons, Saturn's rings, and mountains on our own moon, reinforcing the sheer scale and variety of the universe. Beyond stars and planets, the cosmos is home to immense clouds of gas and dust known as nebulae, which are the birthplaces of new stars. Among the most well-known are the Orion Nebula and the Andromeda Nebula, the latter of which is sometimes visible without a telescope on clear nights. These nebulae function as cosmic nurseries, where forces like gravitational collapse and thermonuclear reactions forge new sources of light and energy. The advent of modern astronomy and space telescopes has revealed a universe of staggering diversity, with billions of galaxies that each contain billions of stars. Many of these stars likely host their own planetary systems, some so remote that their light requires millions or even billions of years to reach us. This means that when you look into the night sky, you are literally gazing into the distant past, witnessing events that unfolded long before humanity's existence. Yet, the universe extends far beyond what our eyes can see, radiating in invisible wavelengths, infrared, ultraviolet, X-rays, and gamma rays that enable scientists to investigate hidden objects. Black holes, for instance, are mysterious phenomena detected only through their effects on surrounding space. Their gravitational force is so immense that nothing, not even light, can escape, presenting a captivating puzzle in the depths of space. Current theories regarding the universe's origin are just as remarkable, with the Big Bang theory positing that approximately 13.8 billion years ago, the entire universe erupted from an incredibly dense and hot state and has been expanding ever since. We can see evidence of this ongoing expansion today by observing the redshift of light from faraway galaxies, which confirms the constant motion of celestial objects in every direction. This cosmic expanse is not just vast, it is also profoundly dynamic, with events unfolding over millions and billions of years. Supernovae, which are the explosions of dying stars, can briefly unleash more energy than an entire galaxy. Astronomers are also investigating enigmatic forces like dark matter and dark energy, which constitute nearly 95% of the universe's mass and energy, yet remain largely unexplained. The early 21st century has marked a new era of space exploration, with achievements that once belonged to science fiction, including the International Space Station, exploratory missions to Mars, and the deployment of next-generation space telescopes. These breakthroughs empower us not just to witness the universe, but to progressively understand the complex processes happening across immense distances, allowing us to appreciate the cosmos in its full splendor. Ultimately, the cosmos is much more than a topic for scientific research. It is a wellspring of inspiration, a means of comprehending our place in existence, and a powerful reminder that we are part of an endless cycle of creation and transformation. As we stand on the frontier of knowledge, we are opening gateways to mysteries that future generations will continue to unravel. Every new discovery, from the dance of planets to the flash of a supernova, reveals the universe as a living, evolving canvas. And so, when you gaze upon the night sky, it may appear as a tranquil and unchanging portrait, but this stillness is an illusion. In reality, that canvas is alive with motion, birth, and change. Stars, planets, and even entire galaxies follow their own life cycles, playing out over millions and billions of years, allowing you to witness firsthand the grandeur and harmony of a cosmos in constant flux. Grasping these cosmic events allows you to sense the sheer scale of the universe and appreciate that you exist inside a dynamic, ever-evolving cosmos. Stars come into being within dense areas of interstellar gas and dust known as nebulae. These vast clouds are primarily composed of hydrogen and helium, occasionally containing trace amounts of heavier elements. Pulled together by gravity, particles of gas begin to collapse, creating dense cores where the internal temperature steadily climbs until it crosses a critical threshold, igniting thermonuclear reactions. This process converts hydrogen into helium and unleashes tremendous energy as light and heat, marking the birth of a new star. Every nebula is distinct in its own right. The Orion Nebula, for instance, is one of the most renowned in our galaxy, and serves as a stellar nursery for hundreds of fledgling stars. In millions of years, these stars will break free from their gaseous cocoon to start their own luminous journeys, perhaps even forming their own planetary systems. Meanwhile, other formations, like the Andromeda Nebula, which you can see from Earth as a faint blur in the night sky, confirm that star creation is a pervasive phenomenon taking place throughout the universe. The genesis of stars is intrinsically connected to the formation of planets. As a protoplanetary disk of gas and dust materializes around a young star, particles within it start to collide and merge, building up into progressively larger objects called planetesimals. These bodies continue to combine, eventually giving rise to planets, asteroids, and comets. In some instances, they become rocky worlds similar to Earth and Mars, while in others, they evolve into gas giants like Jupiter and Saturn. It's fascinating that every cosmic event is dictated by the same laws of physics you can observe and study right here on Earth. Gravity draws matter together, thermodynamics governs heat exchange, and electromagnetic forces generate light and magnetic fields. At the same time, certain events can be purely random, which is why each star and planet possesses its own unique characteristics. Our very own solar system, for example, is the product of a precise set of circumstances that positioned planets in the ideal orbits with the right composition for life to emerge. We should pay close attention to the crucial part that gas and dust play in the assembly of planetary systems. Particles swirling in protoplanetary disks collide in orbit. While some shatter, they more frequently stick together, forming larger bodies. This incremental buildup of material can span tens of millions of years before a fully formed planet takes shape. The presence of elements such as carbon, oxygen, and iron is what determines the chemical blueprint of a future planet, and, by extension, the potential for life to arise there. Magnetic fields also perform a critical function in these cosmic processes. Generated by the motion of charged particles within stars and planets, these fields can heavily influence the formation of atmospheres and the rotation of celestial objects. Earth's magnetic field, for example, shields us from the solar wind, a constant stream of particles flowing from the sun. Without this vital protection, our atmosphere could be eroded away, rendering the conditions for life exceptionally hostile. At times, the formation of planets is punctuated by truly spectacular events. Within the first few million years of a system's life, young planets can collide with one another, creating immense craters and blasting matter back into space. It is widely believed that our moon was formed from such an impact, when a protoplanet roughly the size of Mars slammed into a young Earth, and the ejected debris later coalesced to become our satellite. Stars are rarely born in isolation. They frequently emerge within clusters, which are youthful stellar communities where hundreds or even thousands of stars coexist in close proximity. Eventually, these clusters dissipate, and the stars disperse across the galaxy, enriching it with newly forged elements. These mechanisms help account for the vast array of chemical elements in the cosmos and explain how they are distributed, leading to a rich diversity of planetary systems. Within our solar system, the contrast between the inner rocky planets and the outer gas giants is directly linked to their formation distance from the Sun and the materials available. Inside Jupiter's orbit, gas was quickly swept away, leaving only solid elements behind. At greater distances, however, vast quantities of gas and ice were able to accumulate, forming giant planets with enormous atmospheric envelopes. Modern astronomical missions and observations are consistently confirming these processes, enabling us to study them in remarkable detail. The Hubble Space Telescope, for instance, has delivered stunning images of protoplanetary disks encircling distant stars. At the same time, spectroscopic studies analyze the composition of these disks, helping us predict the nature of future planets. Missions such as Kepler have already identified thousands of exoplanets, each serving as a testament to the varied formation pathways at play throughout our galaxy and beyond. Ultimately, the cosmos is not merely empty space, but a living, dynamic environment, where stars are born and die, planets take shape and evolve, and the universe is in a constant state of flux. Recognizing this truth can help you feel a deeper harmony with the world around you, allowing you to perceive the night sky not just as a scatter of lights, but as a symphony of creation that has been unfolding for billions of years. And as you close your eyes at night, you might remember that every star you can see has undertaken a complex journey of creation and has already made its own contribution to the grand narrative of the cosmos. When most people contemplate the cosmos, their thoughts naturally gravitate toward the solar system. This is our most immediate celestial home, a small portion of the universe that hosts planets, moons, asteroids, comets, and the Sun, the star around which everything orbits. Gaining a better understanding of our solar system's structure and dynamics allows you to more fully grasp the universe's scale and the fundamental processes that shape it. Our solar system took shape approximately 4,500,000,000 years ago from a gigantic cloud of interstellar gas and dust. Due to the force of gravity, this cloud began to contract and rotate, giving rise to the Sun at its center. All the remaining material progressively coalesced over time, eventually forming the planets, asteroids, and comets that we observe today. Ever since its formation, the solar system has maintained a state of relative equilibrium, though its character is continually refined by collisions, cometary impacts, and gravitational disturbances. At its heart lies the Sun, the source of nearly all energy in the system, which exists as a colossal sphere of plasma where thermonuclear fusion transforms hydrogen into helium. This process releases energy that radiates outward, fostering the conditions necessary for life to flourish on Earth. The Sun's immense mass constitutes more than 98% of the entire solar system, and its gravitational pull is what confines the planets to their steady orbits. The inner worlds, Mercury, Venus, Earth, and Mars, are distinguished by their solid, rocky compositions. While they are considerably smaller than the gas giants, this group includes the only planet known to possess conditions suitable for life. Mercury, orbiting closest to the Sun, endures drastic temperature shifts, as it has no atmosphere to regulate them. Venus remains perpetually concealed beneath dense clouds of sulfuric acid, which produce an intense greenhouse effect and surface temperatures that soar above 400 degrees Celsius. Our home, Earth, is defined by its remarkable attributes: vast expanses of liquid water, an atmosphere rich in oxygen, and a climate that has remained stable for billions of years. Earth's magnetic field acts as a shield against the solar wind, while its specific orbit and axial tilt are responsible for the changing seasons that are so essential for life. Mars, often called the Red Planet, is a primary subject of scientific inquiry because evidence suggests it may have once harbored liquid water, making it a plausible destination for future human exploration. Beyond the rocky inner planets reside the gas giants, Jupiter and Saturn, colossal worlds that are dozens of times more massive than our own, and are composed primarily of hydrogen and helium. Jupiter commands the most powerful magnetic field of any planet, and is famous for its massive tempests, including the Great Red Spot, a storm that has been observed raging for centuries. Saturn is renowned for its spectacular system of rings, which are made of ice and rock particles varying in size from microscopic dust to objects several meters across. Even farther out are the ice giants, Uranus and Neptune, which are defined by their frigid temperatures and the bluish hue of their methane-filled atmospheres. These planets also possess strange axial tilts, most notably Uranus, whose axis of rotation is oriented nearly parallel to its orbital plane. Furthermore, they are orbited by intricate networks of moons, some of which are geologically active and may conceal vast oceans of liquid water beneath their frozen surfaces. In addition to these major bodies, The solar system is populated by countless smaller objects, such as asteroids, comets, and meteoroids. You can find the asteroid belt situated between Mars and Jupiter, containing thousands of rocky remnants that were prevented from forming a planet by Jupiter's powerful gravitational influence. Comets, which are mixtures of ice, gas, and dust, trace long, elliptical paths. Their iconic tails, visible from Earth, are formed when their frozen materials vaporize upon approaching the Sun. The planets do not travel along haphazard paths. Their movements are governed by Kepler's laws of planetary motion. Every planet follows an elliptical course, with those farther from the Sun revolving at a slower pace. For instance, Earth takes 365 days to complete its journey around the Sun, whereas Neptune requires almost 16,000 days. These predictable movements create a celestial rhythm that has upheld the system's stability for billions of years. The solar system also engages with the wider galaxy around it. Our system travels through the Milky Way at a velocity of roughly 260 kilometers per second, navigating through diverse regions of interstellar gas and dust. These cosmic journeys can alter the trajectories of comets and asteroids, resulting in long-term cycles of activity and creating the potential for dangerous encounters with Earth. Modern research enables us to investigate not just the planets, but also their moons, rings, and atmospheres in great detail. Spacecraft like the Cassini mission to Saturn, Galileo to Jupiter, and the various Mars rovers have provided invaluable data on the chemical makeup, structure, and geological past of these celestial bodies. Such observations reveal new insights into how our system came to be, and what might be happening in other planetary systems throughout distant galaxies. Ultimately, the solar system is far more than a simple assortment of planets and a star. It is an intricate and lively system where the interplay of gravity, chemistry, and physics dictates cosmic rhythms, generates the conditions for existence, and allows humanity to slowly unravel the universe's greatest secrets. Contemplating this system serves as a reminder of our own planet's beauty and vulnerability, showing us that we are part of a grand cosmic harmony, where every object contributes to the majestic motion of the cosmos. Each planet in our solar system presents a unique environment, but you should pay special attention to those that have both atmospheres and magnetic fields. These unseen forces are pivotal in determining the conditions on a planet's surface, and most importantly, in fostering environments that can sustain life, such as we find on Earth. Grasping their functions helps us realize just how exceptional our world is, and deepens our understanding of cosmic dynamics. Earth's magnetic field is produced by the movement within its liquid iron core, where the motion of charged particles creates what is known as a geodynamo. This field does more than just safeguard the planet from the solar wind, a constant stream of particles from the sun. It also manifests as the brilliant auroras seen near the poles, which you know as the northern and southern lights. Without this magnetic protection, the solar wind would have long ago stripped away Earth's atmosphere, rendering the surface completely inhospitable. When you look at other planets, you can see a wide array of magnetic and atmospheric behaviors. For example, Jupiter possesses the solar system's most formidable magnetic field, which is tens of thousands of times stronger than our own. This diversity illustrates the vast range of physical processes at play and highlights the unique balance of forces that makes life on our own planet possible. This magnetic field generates a vast radiation belt that encircles the planet, while electromagnetic interactions trigger geological and volcanic activity on some of its moons. Both Saturn and Neptune possess formidable magnetic fields as well, though their structures are far more intricate and deviate considerably from the symmetrical field you see on Earth. A planet's atmosphere plays an equally vital role in its environment. On Venus, for instance, a thick shroud of sulfuric acid clouds produces a runaway greenhouse effect, driving surface temperatures above 400 degrees Celsius and creating conditions utterly inhospitable to life. In stark contrast, Mars has an atmosphere so thin it fails to trap any heat, leading to dramatic temperature shifts of hundreds of degrees between day and night. Positioned between these two extremes is our own planet, Earth, where the atmosphere sustains liquid water, stabilizes temperatures, and facilitates air circulation that gives rise to winds, rainfall, and climate patterns. The deep connection between a magnetic field and an atmosphere becomes especially clear when you consider the Moon. Lacking any significant magnetic shield or atmosphere, its surface is perpetually bombarded by the solar wind and cosmic rays. This constant exposure has resulted in a surface blanketed with regolith, a layer of fine dust and rock fragments that is built up over eons, giving the Moon its signature gray appearance. This example truly helps you appreciate just how essential these invisible forces are in defining the conditions on a planet. You can also observe fascinating processes on the gas giants, where winds on Jupiter can gust at several hundred kilometers per hour, forming distinct cloud bands and colossal storms. The rings of Saturn engage in a complex dance with the planet's magnetic field and gravitational pull, leading to the formation of intricate waves and gaps. These powerful processes don't just affect the planet itself, their influence extends to its moons, providing the energy needed to sustain subsurface oceans on icy and volcanically active satellites. It's important to realize that magnetic fields and atmospheres are not static. They are in a constant state of flux, shaped by both internal and external forces. For example, powerful solar flares and coronal mass ejections can temporarily squeeze a planet's magnetosphere, heightening the radiation that reaches its surface. Here on Earth, you see this phenomenon as more intense auroras and disruptions to satellite electronics. On other worlds, these events can be far more extreme, unleashing powerful geomagnetic storms that reshape surface and atmospheric conditions. These dynamic interactions are not confined to planets alone. When asteroids and comets travel through a planet's magnetic field, they are subjected to electromagnetic forces that can shift their trajectories or even cause them to break apart. The solar wind's influence throughout interplanetary space establishes a complex web of interactions, creating the vast heliospheric space that envelops our entire solar system and shields it from galactic cosmic rays. Our scientific investigation into these magnetic fields and atmospheric dynamics is an ongoing endeavor. Missions like Mariner, Voyager, Magellan, along with more recent orbital probes, provide us with the tools to examine the structure of magnetic fields, analyze the chemical makeup of atmospheres, and track the movement of particles. The information from these missions deepens our understanding of how planets form and change, why some hold on to their atmospheres while others do not, and what conditions might foster life. By grasping the sheer complexity of these processes, you start to see that a planet is not merely a rock orbiting a star. Instead, each one is an intricate system of interactions where unseen forces work to create balance and support existence. Magnetic fields and atmospheres are akin to the very breath of these worlds, invisible, yet they define the conditions for everything that exists and moves within their system. Consequently, studying these phenomena helps us better appreciate the uniqueness of Earth and expands our entire perspective of the cosmos. The next time you gaze up at the night sky, or close your eyes to sleep, it's worth remembering that every planet, moon, and even the smallest asteroid is a part of this intricate cosmic symphony, where magnetism, gravity, and the flow of matter weave a tapestry of infinite harmony and beauty. The space you might perceive as calm and empty is, in reality, a stage for incredible dynamics and activity. One of the most stunning displays of this energy is space weather, which encompasses a range of phenomena tied to solar radiation and the way its particles interact with planets, magnetic fields, and atmospheres. The sun is the primary driver of all space weather, emitting not just light and heat but also immense streams of charged particles, a plasma composed of protons, electrons, and helium ions. This flow of particles is known as the solar wind, and it travels at incredible speeds, eventually reaching the planets of our solar system and engaging with their magnetic fields and atmospheres. Solar flares are abrupt explosions of energy from the sun's surface, which release powerful bursts of X-rays and ultraviolet radiation. During the most intense flares, massive clouds of plasma called coronal mass ejections can erupt into space, carrying millions of tons of solar material along with them. When one of these clouds slams into a planet's magnetosphere, it can trigger magnetic storms that amplify auroras, disturb the ionosphere, and even interfere with satellite operations and communications on the ground. Earth is largely shielded from the solar wind by its magnetic field, but during particularly strong solar events, particles can breach the upper layers of our atmosphere and provoke geomagnetic storms. These storms can disrupt navigation, radio signals, and power grids. A famous historical case is the storm of March 18, 1859, which caused telegraph systems across Europe and North America to fail due to the intense solar activity. Other planets also feel the effects of space weather, though often in very different ways. On Mars, which has a very thin atmosphere and almost no magnetic field, the solar wind strikes the surface directly, slowly stripping atmospheric particles away into space. It's highly probable that this very process is responsible for the loss of most of Mars's atmosphere over billions of years. With their immense magnetic fields, planets like Jupiter and Saturn generate colossal radiation belts. Within these belts, particles are accelerated to tremendous energies, which in turn fosters extreme environments for their moons and produces some truly unique light phenomena that you can observe. It's fascinating to realize that space weather has an impact that extends beyond just the immediate physical state of a planet. It actually shapes the long-term development of atmospheres and climates. For instance, solar winds can trigger chemical reactions in the upper atmospheric layers, which results in the creation of ozone and ionized layers, processes that help to stabilize the atmosphere and shield the surface below from cosmic radiation. To keep an eye on this space weather, we rely on a fleet of satellites and probes. Spacecraft missions, including SOHO, ACE, STEREO, and the Parker Solar Probe, are constantly gathering data on the solar wind's velocity, the density of its particles, its magnetic fields, and overall solar activity. This stream of information enables us to predict geomagnetic storms, investigate solar processes, and better grasp how space weather dictates the conditions for life, not just on Earth, but on other worlds as well. Beyond solar winds and flares, you should also know that space weather encompasses galactic cosmic rays, which are high-energy particles that originate from far outside our solar system. While their effect on Earth is less pronounced compared to the solar wind, these rays do contribute to the ionization of our atmosphere, and could potentially influence cloud formation and climate shifts over vast geological timescales. These interconnected processes ensure that our solar system is a dynamic and living place. Every single planet is under the constant influence of space weather, which sculpts its atmosphere, magnetosphere, climate, and in some cases even its geological activity. Gaining a deeper understanding of these interactions reveals new avenues for research and better equips us for future human missions, especially to planets and moons with the most extreme conditions. Therefore, you can think of space weather as an unseen yet mighty force that shapes the conditions for life, governs the movement of particles, and drives atmospheric phenomena on every planet. It serves as a constant reminder that space is never static. Instead, it is an ever-evolving system where energy, matter, and motion combine to forge unique circumstances for each and every world. You'll find that the planets of our solar system are very seldom alone. The majority are orbited by moons, which range from small asteroid-like bodies to enormous worlds that rival Mercury or Mars in size. These moons are far more than simple decorative objects in the sky. Many of them exhibit their own geological activity, possess atmospheres, and even hide subsurface oceans. Take Jupiter, the largest planet in our solar system, which is accompanied by a multitude of moons, 4 of which are particularly noteworthy: Io, Europa, Ganymede, and Callisto. Io is a world of fire, home to over 400 active volcanoes that erupt with sulfurous gases and molten magma. Its incredible volcanic nature is fueled by Jupiter's tidal forces, which continuously stretch and compress Io's core, creating heat and ensuring its surface is in a constant state of geological renewal. Europa, Io's neighbor, is remarkable for the liquid ocean concealed beneath its frozen crust. We have evidence for this ocean from observations of fractures in the ice that look much like Earth's glaciers, and from its magnetic field, which points to the existence of salty water below. This hidden ocean might hold more water than all of Earth's oceans combined, making it one of the most compelling locations in the search for life beyond our home planet. Ganymede, which is the largest moon in the entire solar system and is even bigger than the planet Mercury, generates its own magnetosphere. This magnetic field interacts with Jupiter's, producing a complex system of radiation belts and auroras. Callisto, a more distant moon, is a world covered in ancient ice and countless craters, perfectly preserving a pristine history of cosmic impacts. This variety among the moons of a single planet truly shows you how different worlds can be, even when they are orbiting the very same gravitational center. Saturn and its family of moons display a similarly stunning diversity. Enceladus, a tiny, icy moon, features enormous geysers that blast water vapor and ice particles out into space. These plumes feed into Saturn's ring system and strongly suggest the presence of a subsurface ocean that could potentially support life. Titan, Saturn's biggest moon, is another world of great interest, possessing a thick, nitrogen-rich atmosphere, along with lakes and rivers of methane. This unique environment makes Titan a primary focus of study, particularly because its conditions are thought to resemble those of Earth's own early atmosphere from billions of years ago. Even around Uranus and Neptune, you find moons with their own fascinating activity. Triton, Neptune's largest moon, orbits in the opposite direction of the planet's rotation and has geysers of nitrogen ice that shoot material into its thin atmosphere. These features offer clues about the history of captured objects that might have come from the outer solar system, perhaps originating in the Kuiper belt. Even the smallest moons present unique characteristics that I find compelling. Certain asteroid-like satellites possess irregular shapes, generate very weak gravitational fields, and occasionally show signs of compression and cracking due to tidal forces. Observing these smaller bodies allows scientists to model the evolution of celestial objects and learn how they interact with planets and with each other. Studying the geological activity of moons is critical, not just for space science, but also for planning our future expeditions. When you understand their surfaces, internal structures, and potential for subsurface oceans, it helps in developing strategies for landing, exploration, and even potential colonization. For example, missions are being planned to Europa and Enceladus specifically to investigate their subsurface oceans and look for signs of life, with robotic probes and deep ice drilling systems. Moreover, the geological activity of these moons directly impacts the planets they orbit. Io's volcanism, for instance, creates streams of particles that interact with Jupiter's magnetosphere, resulting in brilliant auroras. Meanwhile, the geysers on Enceladus replenish Saturn's rings by supplying new particles and modifying their structure. In this way, moons are not just passive companions, but active players in the dynamics of their planetary systems, which I think makes the study of them incredibly rewarding. Every moon you see is an entirely separate world, complete with its own unique history, internal mechanics, and unresolved mysteries. By studying them, we broaden our knowledge of geology, atmospheric phenomena, and the chances of life emerging in the most surprising environments. For me, understanding the geological activity on these moons is the very key to unlocking how planets and their surrounding systems originally formed and subsequently evolved. From volcanic landscapes to subterranean oceans of ice, each moon holds unique cosmic secrets, demonstrating that life and the movement of matter can appear in an incredible variety of forms. Space, as you know, is filled with more than just planets and their satellites. It's also teeming with innumerable smaller objects like asteroids and comets, which hold the clues to deciphering the solar system's origins. These bodies may seem small and insignificant, but they exert a tremendous influence on the evolution of planets, the dynamics of orbits, and even the very conditions that allow for life here on Earth. I often describe asteroids as solid celestial objects, primarily composed of rock, metal, and various mineral impurities, with sizes that can span from just a few meters to hundreds of kilometers across. The majority of these are clustered within the belt situated between Mars and Jupiter, acting as a sort of dividing line, a collection of leftover primordial material from planetary formation. I consider these objects to be fossils of our solar system, as they preserve the chemical makeup and structure from its birth, some 4.5 billion years ago. Comets, on the other hand, are quite different from asteroids. They are made up mostly of ice, dust, and frozen gases like water, ammonia, and methane. As a comet nears the Sun, the intense heat causes its ices to vaporize. This process creates the distinctive gas and dust tails that always point away from the Sun, which can stretch for millions of kilometers and produce breathtaking sights in our night sky. It was these comets that first alerted scientists to the way sunlight interacts with water vapor and other gases, which is fundamental to how planetary atmospheres are formed. The paths that asteroids and comets follow are dictated by their gravitational interactions with the planets and the Sun, and sometimes these trajectories bring them into Earth's orbit, where they become potential meteorites. When these objects survive their descent and land on the surface, they deliver material with an ancient chemical signature. This allows my colleagues and me to analyze the composition of the early solar system and hunt for organic compounds that could have been the original ingredients for life. History offers us many examples of asteroid and comet impacts on Earth. Perhaps the most well-known is the collision with an asteroid measuring about 10 kilometers in diameter, which took place approximately 66 million years ago. This single event triggered worldwide climate shifts and led to the mass extinction of the dinosaurs and countless other species, proving just how profoundly these smaller bodies can redirect the course of a planet's history. Objects arriving from the outer solar system are just as compelling to me. Asteroids originating from the Kuiper Belt and the Oort cloud follow highly unusual orbits and possess compositions that often distinguish them from bodies closer to us. By studying them, you and I can learn about the formation processes of the outer solar system and the great migrations of the planets. These distant travelers include both rocky bodies and frozen comet-like objects that are rich in organic compounds. To study all this, we use modern methods of observation and research that range from ground-based telescopes to orbital observatories and interplanetary probes. Missions you may have heard of, such as OSIRI-SREX, Hayabusa, and Rosetta, are designed to study asteroids and comets at close range, even bringing samples back to Earth for detailed laboratory analysis. These missions provide us with crucial data on the composition, structure, and evolution of celestial bodies, clarifying their role in planet formation and the possible delivery of organic matter through space. One of the most fascinating aspects of asteroids is their sheer diversity. Some of these objects have irregular shapes and might be hollow or shattered into fragments. Others are rich in metals that could one day become valuable resources for our future space missions. Furthermore, by studying the trajectories and dynamics of these bodies, we are developing strategies to protect Earth from potentially hazardous impacts, which include methods for deflecting or even destroying threatening asteroids. Beyond their beauty and the scientific questions they raise, comets are also instrumental in the cosmic transport of water and organic materials. The idea that a portion of Earth's water was originally delivered by comets is a hypothesis that remains a very active area of my research field. By examining the composition of comets, especially the isotopic ratios of hydrogen and oxygen, we can refine our models of how Earth's atmosphere and its vast oceans came to be. So you see, asteroids and comets are far more than just minor objects set against a backdrop of giant planets. They are the custodians of our solar system's history, active players in its ongoing dynamics, and potential couriers of life's essential components. Observing them and studying their composition and trajectories opens up new avenues for understanding cosmic evolution, the interconnectedness of planets, and the critical role that small bodies play in the fate of Earth and other worlds. These enigmatic objects prove that even the smallest bodies can have an enormous impact, reminding us that space is in perpetual motion, where every single object, no matter its size, fulfills a unique purpose. Many planets in our solar system possess rings, but the most renowned and thoroughly studied are, of course, those belonging to Saturn. I want you to understand that planetary rings are not merely decorative features. They are dynamic systems, made up of billions of particles of varying sizes and compositions, all interacting with one another and with the planet's gravitational field. These rings can be composed of ice, rock, and dust, with particles ranging from microscopic specks to boulders several meters in diameter. The particles within these rings are in a state of constant motion, where they collide, fragment, and reassemble into new structures. These ongoing processes give rise to an incredible variety of forms, from dense, brilliant rings to faint, transparent shells that are nearly impossible to see from Earth. Saturn serves as the quintessential example of a planet with an exceptionally complex and prominent ring system. Its main rings are designated A, B, and C, and they are accompanied by several thinner, more diffuse rings. Our scientific observations reveal that Saturn's rings are incredibly dynamic, constantly changing over time to form waves, spiral patterns, and distinct gaps. You might be fascinated to learn that these beautiful structures are shaped by gravitational resonances with Saturn's moons. These moons influence the particles, either speeding them up or slowing them down, which in turn carves out the intricate designs you see. While Saturn's rings are famous, other planets like Jupiter, Uranus, and Neptune possess rings of their own, though they are far more subtle and less conspicuous. Jupiter's rings, for instance, are primarily composed of fine dust particles generated from impacts on its small inner moons. If you were to look at the rings of Uranus and Neptune, you would find them to be much darker and more diffuse. However, they still display complex features, including very narrow gaps and concentrated bands, which are also sculpted by the gravitational pull of nearby small moons. The origin of planetary rings remains one of the more compelling mysteries in astronomy, and I find there are several leading ideas. One hypothesis suggests that rings are the leftover debris from moons that were shattered by a planet's immense tidal forces. An alternative theory proposes that they are the remnants of the primordial gas and dust disk from which the planet itself originally condensed. Regardless of how they came to be, what these rings show us is a beautiful interplay of gravity, particle dynamics, and tidal forces. The behavior of particles within the rings is astonishingly complex. They constantly collide, leading to both their fragmentation and their clumping into temporary clusters. The gravitational influence of moons creates density waves that ripple through the rings, functioning much like tides on Earth but on a miniature and simplified scale, demonstrating that even these smaller systems have remarkably sophisticated internal mechanics. Interestingly, rings are not just showcases of particle physics. They also serve as invaluable tools that help researchers like me study the planets themselves. You can learn a lot by observing them, as shifts within the rings can signal the movement of moons, variations in the planet's mass, or even reveal the existence of yet undiscovered objects. Observing these ring systems gives us insight into the physical processes at play near a planet, from interactions with its magnetosphere to its atmosphere and particle streams. Furthermore, rings can act as a reservoir of material for the birth of new moons. I've studied theories suggesting that some of the smaller moons may have coalesced from ring particles, gradually gathering enough material to form stable orbiting bodies. In this way, you can see rings as a dynamic system, a natural physics laboratory in space, and a nursery for planetary satellites all at once. Beyond Saturn, the ring systems of Jupiter, Uranus, and Neptune allow scientists to investigate the varied conditions under which rings form and interact with gravitational fields. These comparative studies help us understand why rings can remain stable over millions of years, what forces might eventually tear them apart, and how they affect the orbital dynamics of their host planets. Spacecraft missions such as Cassini, Voyager, and other orbital probes planned for the future provide an unparalleled chance to examine these rings up close. Instruments like cameras and spectrometers gather crucial data on the composition, temperature, and motion of the particles, enabling us to construct a detailed map of the ring's structure and uncover elements that were previously unknown. So, as you can see, planetary rings are far more than just beautiful ornaments encircling distant worlds. They are profoundly complex and dynamic systems that reflect the cosmic dance of matter, gravity, and motion. They offer us a glimpse into the very processes that formed planets and their moons billions of years ago, and help us appreciate just how diverse and active the cosmos truly is. Now, let's turn our attention to the magnetic fields of planets, which are invisible yet crucial structures. They provide a protective shield for atmospheres, shape space weather, and are responsible for the spectacular phenomenon of the polar auroras. These fields originate from the motion of conductive fluid within a planet's core, which generates a complex network of magnetic field lines that stretch far out into space, forming a region known as the magnetosphere. For example, Earth's magnetic field is what safeguards our atmosphere from the erosive power of the solar wind, a constant stream of charged particles flowing from the sun. When these solar particles encounter our planet's magnetic field, they are funneled toward the poles. There they collide with atmospheric gases and create the auroras, which you may know as the northern and southern lights. These displays are not merely beautiful, they are the visible evidence of the immense energy being exchanged between the sun and our world. Among all the planets in our solar system, Jupiter boasts the most powerful magnetic field. Its magnetosphere is so vast that it extends tens of times the planet's own radius, reaching even beyond the orbit of Saturn. This immense field traps particles from the solar wind and accelerates them to astonishing speeds, forming intense radiation belts. I have to emphasize that this presents a considerable danger for space missions, as the high-energy radiation can severely damage electronics and pose a threat to any future astronauts. Saturn also possesses a formidable magnetic field, although it isn't as strong as Jupiter's. Its magnetosphere interacts with its famous rings and moons, which results in intricate particle currents and the generation of auroras at its poles. Uranus and Neptune, on the other hand, have peculiar, highly tilted magnetic fields. This orientation leads to unstable and constantly shifting interactions with the solar wind, showing us that magnetospheres can have a wide variety of forms and behaviors that reflect a planet's internal workings. I believe the interaction between magnetic fields and the solar wind is absolutely critical for a planet to retain its atmosphere. Consider Mars, where the absence of a global magnetic field has allowed the solar wind to slowly strip away its atmospheric gases over eons, leaving it with the thin, nearly non-existent atmosphere it has today. This starkly illustrates how vital a magnetic field is as a protective planetary shield, and how it influences the potential for life. The intensity of a planet's magnetic field is determined by several factors, including its rotation speed, the chemical makeup of its core, and its internal temperature. Planets like Earth and Jupiter, which have liquid metallic cores, are capable of generating very strong magnetic fields. In contrast, planets with solid or poorly conductive cores tend to have either very weak fields or none at all. By studying these mechanisms, scientists can create better models of planetary evolution and understand how planets protect their atmospheres. Ultimately, the auroras you might see are the visible manifestation of the clash between a planet's magnetic field and the solar wind. Particles, energized and guided by the magnetosphere, slam into atoms and molecules high in the atmosphere. This collision excites the atmospheric particles, causing them to emit light and glow, painting the sky with brilliant colors that reveal the invisible forces at work. You can see that different elements are responsible for distinct auroral colors. For instance, oxygen generates hues of green and red, whereas nitrogen is the source of purple and blue light. These breathtaking displays are not exclusive to our planet, as you can also witness them on Jupiter, Saturn, and Uranus, where the auroras can shine with an intensity tens of times greater than those on Earth. Magnetic fields also serve as a crucial tool for scientists aiming to understand the internal architecture of planets. By analyzing magnetic field data collected from orbiting spacecraft, it becomes possible to deduce the size of a planet's core, the velocity of its internal convection currents, and the makeup of its deep layers. In this way, an invisible magnetic field provides you with a method for probing planetary depths that are otherwise completely inaccessible to direct observation. Future explorations planned for Jupiter, Saturn, and Mars will involve in-depth investigations of their magnetospheres and how they interact with the solar wind. This research will enhance our comprehension not only of the field's protective capacity, but also of its effects on orbital systems, moons, and planetary atmospheres. Grasping these complex processes is also vital as you prepare for long-term space missions and the possibility of colonizing other planets, where shielding against cosmic radiation is of paramount importance. Consequently, planetary magnetic fields are much more than simple protective shields or the origin of auroras. They are fundamental components in the dynamics of our solar system. They reveal how unseen forces can sculpt the surface, atmosphere, and climate of worlds, while also impacting both life and technology. As you study these fields, our collective understanding expands regarding how planets engage with the surrounding space and how the sun's energy is distributed throughout the entire system. Space weather is the term for the dynamic conditions originating on the sun and in its immediate vicinity that have a direct impact on the planets, including Earth. These phenomena, which encompass solar flares, coronal mass ejections, and shifts in the solar wind, generate effects that are both visible and invisible, yet are distinctly felt both here on our planet and out in space. Solar flares are abrupt, powerful releases of energy within the sun's atmosphere, triggered by intense magnetic activity. The energy they unleash can be equivalent to billions of megatons of TNT, and this is coupled with a flood of radiation across the full electromagnetic spectrum, which includes X-rays and ultraviolet light. When you observe the effects of solar flares on Earth, they typically appear as interruptions in radio communications, glitches in satellite electronics, and more vivid polar auroras. Coronal mass ejections involve the expulsion of enormous clouds of plasma from the sun's surface into the vastness of interplanetary space. These clouds can travel at speeds reaching up to 2,000 kilometers per second, and upon colliding with planetary magnetospheres, they can set off powerful geomagnetic storms. For you on Earth, these events can modify currents in the ionosphere, interfere with navigation systems, and even produce magnetic irregularities. The solar wind is a perpetual outflow of charged particles that streams from the sun in all directions. As it encounters planetary magnetic fields, It molds their magnetospheres and establishes the conditions necessary for polar auroras to occur. During times of heightened solar activity, the solar wind intensifies, thereby elevating the probability of geomagnetic storms, which can then lead to voltage fluctuations in power grids, widespread magnetic disturbances, and alterations in radio signal transmissions. It is fascinating how closely space weather is tied to the cycles of solar activity, which recur approximately every 11 years. Throughout these cycles, the Sun transitions between periods of minimum and maximum activity, which in turn influences the frequency of solar flares, the power of coronal mass ejections, and the regularity of geomagnetic storms that you experience on Earth. Understanding these patterns is essential for forecasting space weather and reducing its potential harm to our technology and daily lives. Space weather is also investigated using a combination of ground-based observatories and instruments in orbit. Satellites like the Solar and Heliospheric Observatory, or SOHO, the Solar Dynamics Observatory, or SDO, and the Parker Solar Probe maintain a constant watch on the Sun. They measure particle flows and magnetic fields, supplying us with detailed information on the dynamics of solar activity, which allows you to develop predictive models for space weather that are critical for the safety of astronauts and satellite operations. Here on Earth, the influence of space weather extends beyond just the polar auroras to impact our atmospheric processes. Variations in the ionosphere can disrupt the propagation of radio waves, interfere with Global Positioning System or GPS signals, and affect the functioning of radar systems. In more severe instances, geomagnetic storms have the capacity to trigger widespread power grid failures, which demonstrates just how interconnected solar events are with modern life on our planet. Significant focus is now being placed on researching how space weather affects human health and the technologies of the future. Astronauts on long missions beyond the protection of Earth's magnetosphere are exposed to high levels of radiation. This reality makes it imperative that you develop advanced shielding systems and carefully plan missions to align with the Sun's activity cycles to ensure crew safety. Ultimately, space weather represents a complex web of interactions that connects the Sun, interplanetary space, and the planets. It shows you how the energy from a single star radiates across immense distances, directing the motion of particles and shaping planetary atmospheres and magnetic fields. Studying these phenomena not only helps you to decipher the nature of solar activity, but also drives the innovation needed to shield humanity from its potentially damaging consequences. Observing the cosmos is the very bedrock of astronomy, a practice that enables you to comprehend the structure of the universe and the fundamental laws that govern it. From our earliest history, humans have looked to the sky with their own eyes and simple tools to watch the stars and planets, progressively creating the sophisticated technologies that now allow us to gaze into the most remote regions of space. Optical telescopes marked the first revolutionary leap in the field of observational astronomy. These instruments function by gathering light through lenses or from mirrors, and then concentrating it for detailed analysis. Today's advanced optical telescopes, epitomized by the Hubble Space Telescope, give you the ability to view objects that are billions of light-years away, unveiling the structures of galaxies, stars, and nebulae with astonishing clarity. By using optical observations, you can appreciate how astronomers have uncovered new planets, located worlds outside our solar system, and analyzed both star clusters and the very structure of galaxies. A revolutionary method for observing the universe emerged with radio telescopes, which employ radio waves that can pierce through cosmic dust and gas clouds impenetrable to optical light. These powerful instruments allow us to investigate cold hydrogen clouds, the hearts of galaxies, and the cosmic microwave background radiation, which is the afterglow of the Big Bang. Thanks to radio astronomy, we have unraveled the structure of our own Milky Way, found pulsars, which are rapidly spinning neutron stars that emit precisely timed radio pulses, and examined the intense activity of black holes at the core of galaxies. In contrast, infrared telescopes grant you a view of warm celestial objects that are otherwise concealed within cosmic dust, such as regions where new stars are actively forming. For instance, observatories like the Spitzer and the James Webb Space Telescopes have delivered stunningly detailed images of protostars and the disks that surround them, directly showing you how new worlds come into being. These particular observations are crucial for helping us grasp how stars and planets emerge from vast clouds of gas and dust, and how the essential conditions for life might develop. Meanwhile, telescopes sensitive to ultraviolet and X-ray light have pulled back the curtain on the universe's most high-energy phenomena. They let you witness supernova explosions, neutron stars, the swirling accretion disks around black holes, and the incredibly hot gas that permeates clusters of galaxies, revealing the cosmos in energies far beyond what the human eye can perceive. Modern observatories now frequently merge the capabilities of different telescopes and spectrometers, enabling multispectral analyses of celestial objects. By combining this data, you get a far more complete picture of the physics governing stars, planets, galaxies, and the vast spaces between them. For example, observing an object simultaneously in optical, infrared, and X-ray light helps us comprehend the complex structures of stellar winds, massive ejections, and powerful magnetic fields. Furthermore, telescopes employing interferometry, such as the Atacama Large Millimeter/Submillimeter Array, or ALMA radio interferometer, and the Very Large Telescope Interferometer, or VLTI, project, combine signals from multiple locations on Earth. This process creates images with a resolution so high, it's like using a single colossal telescope thousands of kilometers in diameter. These advanced technologies have enabled you to see the intricate structures surrounding black holes and the disks of forming stars, in a level of detail that even the largest individual telescopes cannot achieve. Placing observatories in orbit has allowed us to bypass the image-distorting effects of Earth's atmosphere. The Hubble Space Telescope, for instance, delivered an unprecedented level of clarity in its images, empowering us to see billions of distant stars, galaxies, and the formation of the very first stars. The James Webb Space Telescope has since extended our reach into the infrared spectrum, letting you peer into the most remote and obscure corners of the universe where new stars and planets are currently being born. Exploring the universe with this diverse array of telescopes has demonstrated that space is vastly more intricate than we ever imagined. These instruments have exposed the fundamental processes that dictate the life and death of stars, the creation and collision of galaxies, the birth of planets, and the profound impact of energy on interstellar space. It is through these astronomical observations that humanity can witness the cosmos as it truly is, from the depths of nearby nebulae to the most distant quasars, effectively charting the boundless expanse of space and time. Essentially, telescopes and astronomical observations are your windows to the cosmos, through which we can decipher its laws, its dynamics, and its history. They not only empower us to discover new objects, but also to understand the physics behind the forces that shape the universe. This creates a vital link between humanity and the infinite, solving mysteries that range from our neighboring stars to the most faraway galaxies. The study of exoplanets, planets existing beyond our own solar system, has emerged as one of the most captivating frontiers in contemporary astronomy. Since the very first confirmed exoplanet was identified late in the 20th century, you have seen scientists catalog thousands of worlds orbiting other stars. Each discovery presents unique characteristics and offers a new opportunity to understand the processes that lead to the formation of planetary systems. There is a wide variety of methods used to detect these distant worlds. The transit method, for example, involves watching for tiny periodic dips in a star's brightness, which occur when a planet crosses in front of it. This technique has led to the discovery of thousands of exoplanets, and helps you determine their sizes and orbital paths. Another approach, measuring a star's radial velocity, detects the slight wobble caused by the gravitational tug of an orbiting planet, allowing us to calculate its mass and orbital properties. Exoplanets are generally classified into several distinct categories based on their properties. You have hot Jupiters, which are massive gas giants orbiting extremely close to their parent stars, with surface temperatures that can climb to several thousand degrees. Super-Earths are planets more massive than our own but less massive than Neptune, and they are of great interest because they might possess solid surfaces. Then there are Earth-like exoplanets, which are worlds with sizes and masses comparable to Earth's, potentially hosting atmospheres and liquid water, thereby creating conditions suitable for life. A primary objective in this field is the search for exoplanets within the habitable zone, that specific region around a star where conditions might allow for liquid water to exist on a planet's surface. The presence of water is widely regarded as a fundamental requirement for life as we understand it. Such planets could have climates favorable for the emergence of biochemical processes, and you can analyze their atmospheres and surfaces with spectroscopy to hunt for telltale signs of water, oxygen, methane, and other biosignatures. Many exoplanets have been found within systems that contain multiple planets, resulting in complex and dynamic orbital arrangements. These systems give you invaluable insights into how planetary systems form, how planets migrate over time, and how they interact with the leftover material from their protoplanetary disk. For instance, a system like TRAPPIST-1, which features several Earth-sized planets within its habitable zone, has become a focus of intense scientific scrutiny. Studying the atmospheres of these distant worlds is now possible using spectroscopic observations, especially when a planet transits or passes in front of its host star. When light from a distant star filters through a planet's atmosphere, it is altered in a way that produces a spectrum containing distinctive absorption bands. A thorough analysis of these bands allows scientists to ascertain the atmosphere's chemical composition, revealing the existence of clouds, water vapor, carbon dioxide, and methane, which in turn offers vital clues about the planet's climate and its potential to harbor life. The database of known exoplanets is continuously being enlarged by modern missions such as the Kepler Space Telescope, TESS, and the James Webb Space Telescope. While Kepler found thousands of planets via the transit method, and TESS persists in surveying nearby stars, the James Webb Telescope delivers exceptional precision in examining the atmospheres of specific exoplanets using infrared spectroscopy, enabling a deep analysis of their chemical profiles and possible biosignatures. A planet's potential habitability depends on far more than just its proximity to a star. It is also determined by its rotation, axial tilt, magnetic field, atmospheric content, and the presence of liquid water. Planets that possess strong magnetic fields are capable of shielding their atmospheres from the erosive effects of stellar wind, which helps to preserve water and maintain conditions favorable for life. A careful assessment of these elements is crucial for gauging the probability of life beyond our solar system and for directing the course of future research missions. Therefore, the investigation of exoplanets opens up new frontiers in the search for extraterrestrial life and enhances our understanding of the formation and evolutionary processes of planets. Each newly found world serves not merely as a subject for observation, but as a vital clue to deciphering the uniqueness of Earth, the immense diversity of planetary systems, and the conditions that might allow life to emerge in the universe's most remote regions. Stars represent the essential building blocks of the cosmos, providing light to galaxies and shaping the conditions necessary for the formation of planets. Their birth originates in giant molecular clouds, which are vast collections of gas and dust extending for tens or even hundreds of light years and acting as stellar nurseries. These clouds are composed mainly of hydrogen, supplemented with helium, carbon, oxygen, and other elements. Under the effect of gravitational instabilities, shock waves from supernova explosions, or internal turbulent motions, these clouds begin to experience localized compressions that form dense cores. It is these cores that eventually collapse under their own gravitational pull, giving rise to what are known as protostars. The protostellar stage is the interval during which the compressed core of gas has not yet ignited thermonuclear reactions in its center. A protostar is typically encircled by a rotating disk of gas and dust, which provides the raw material for the eventual formation of planets, asteroids, and comets. The radiation emanating from the protostar progressively heats this disk, creating a flow of photons that rearranges the gas and establishes the preliminary conditions for a future planetary system. When the pressure and temperature at the protostar's center reach a critical point, the thermonuclear fusion of hydrogen into helium commences. This event signifies the birth of a complete main-sequence star, which will act as a source of light and energy for millions or billions of years. A protostar's mass dictates its entire future. More massive stars lead short, brilliant lives, while their less massive counterparts generate stable radiation over billions of years. The process of star formation is also marked by the expulsion of matter through jets and outflows that emanate along the protostar's axis of rotation. These outflows engage with the surrounding interstellar medium, generating shock waves that are visible as luminous clouds in optical and infrared light. In doing so, they clear out the area around the protostar, sweeping away surplus gas and dust, and creating an open region conducive to planet formation. Stars seldom come into being alone. They are typically born inside clusters of tens, hundreds, or even thousands of stars that are held together by gravity. Such clusters constitute a dynamic setting where interactions among stars and gas clouds mold the evolution of each object, at times leading to the migration of planets or the outright destruction of their protoplanetary disks. A star's mass is the determining factor for its entire life story. The most massive stars exhaust their fuel supplies very quickly, living for only a few million years before ending their existence in a supernova. Medium-mass stars like our Sun have lifespans of billions of years, expanding into red giants after their hydrogen fusion ceases, and ultimately contracting into white dwarfs. Smaller red dwarfs, however, can burn for tens of billions of years, providing stable radiation and potentially fostering long-term conditions for life to evolve on their planets. Observing star-forming regions with infrared and radio telescopes enables the study of cloud density, temperature, and chemical composition. These observations reveal how stars of different masses are born, how protostellar disks mature, and what kinds of environments are established for future planets. Modern research has even detected complex organic molecules, including precursors to amino acids, inside protostellar clouds, raising the possibility that the chemical preconditions for life can exist even before planets have fully formed. In summary, the creation of stars is a complex and dynamic sequence of events, starting with the collapse of gas clouds and ending with a stable star that radiates light and energy. This entire process provides the foundation for the emergence of planets, solar systems, and potential life, illustrating how order and structure can arise from chaos and gravity in the cosmos. Every star that ignites in the vastness of space becomes a new beacon of light and warmth, exerting its influence on the cosmic environment for millions of light years in every direction. The life cycle of a star is a compelling tale of transformations that showcases how the universe evolves over time. A star's mass determines its evolutionary path and the manner of its death, which in turn affects the surrounding space by creating new chemical elements essential for future planets and life. When a star of average size, such as our Sun, depletes the hydrogen in its core, it begins its transformation into a red giant. As a star ages, its inner layers collapse due to gravity, while its outer layers balloon outward, producing an immense and luminous glow. This expansion causes the surface temperature to fall, lending the star a reddish appearance, as the core heats up enough to begin the thermonuclear fusion of helium into carbon and oxygen. This phase is also marked by the expulsion of matter into the cosmos, which creates nebulae containing the very elements required for new stars and planets to form. For stars of much greater mass, this evolutionary journey unfolds far more quickly. They burn through their fuel supply millions of times faster than their smaller counterparts, progressing through a sequence of stages that forge heavy elements like carbon, oxygen, neon, silicon, and finally, iron. Once iron builds up in the core, fusion reactions come to a halt, causing the star to lose its internal support against gravity and undergo a catastrophic collapse. This implosion rebounds into a supernova, an astonishingly brilliant explosion that can momentarily outshine its entire galaxy. The blast disperses heavy elements throughout space, enriching the interstellar medium with the carbon, oxygen, and iron essential for creating new stars, planets, and potentially life. The destiny of the star's core remnant is determined by its mass, resulting in either a neutron star or a black hole. For stars of average mass, the final evolutionary stage is a white dwarf. These are the dense, hot cores left over after the star has shed its outer layers into space. Over billions of years, white dwarfs steadily cool down, fading in brightness and energy. Yet they persist as powerful testaments to the stars they once were. Even without active fusion, studying them helps astronomers decipher stellar composition and trace the history of chemical enrichment in our galaxy. Following the titanic explosions of massive stars, neutron stars and pulsars can be formed, which are objects composed of incredibly dense matter with powerful magnetic fields. Pulsars emit highly regular radio waves that can be detected from Earth, functioning as natural cosmic lighthouses. These signals enable scientists to investigate the properties of space and time, while also testing the limits of theories on gravity and quantum mechanics. The life cycle of stars is fundamentally linked to the creation of planetary systems and the necessary conditions for life. The shock waves from supernova explosions compress vast clouds of gas, triggering the formation of new stars. These clouds, now seeded with a rich diversity of elements, provide the foundational material for planets, including those that might possess water and organic molecules. By observing stars across all phases of their existence, astronomers can construct detailed models of stellar evolution, forecast cosmic events, and gain a deeper understanding of the processes that govern our galaxy and the universe. Modern observatories, equipped with X-ray and infrared instruments, allow us to view everything from nascent stars to ancient white dwarfs, illustrating the perpetual cycle of matter's birth and transformation. Ultimately, stellar evolution is a grand narrative of transformation, interaction, and cosmic rebirth. Celestial phenomena like red giants, white dwarfs, and supernovae not only dictate the dynamics of galaxies, but also forge the chemical elements required for new stars, planets, and life to emerge. Upon completing its journey, every star imparts a legacy that shapes the future of the cosmos, demonstrating the infinite recycling of matter and energy. Among the most enigmatic and formidable objects in the universe are black holes, which possess the power to fundamentally warp the fabric of space and time. They are born from the remnants of massive stars whose cores have collapsed, creating gravitational fields so intense that nothing, not even light, can escape. A black hole's defining feature is its singularity, a point of infinite density, which is shrouded by an event horizon, the boundary of no return. Because black holes cannot be observed directly, astronomers must rely on indirect evidence to confirm their existence. These methods include tracking the orbits of stars around an unseen massive object, detecting powerful X-ray emissions from superheated material in accretion disks, and capturing the faint ripples of gravitational waves generated by black hole collisions. Black holes are found in a wide range of sizes. Stellar mass black holes are forged from the collapse of a single massive star, and typically have masses several times that of our Sun. At the heart of most galaxies, however, lie supermassive black holes, which can weigh millions or even billions of times more than the Sun. Their origins are still debated, but they may have formed alongside their host galaxies, or grown by consuming smaller black holes and vast quantities of matter over cosmic time. Surrounding a black hole, an accretion disk is formed from matter spiraling inward under the pull of intense gravity. As this material gets closer, it heats up and unleashes tremendous amounts of energy, often as X-rays and gamma rays, which allows us to see active galactic nuclei from across the universe. Additionally, powerful jets of matter can be ejected from the black hole's poles, extending for thousands of light years, and profoundly influencing star formation within the galaxy. Black holes are also a primary source of gravitational waves, which are ripples in spacetime that travel at the speed of light. The mergers of these cosmic giants are now being detected by specialized observatories, like the Laser Interferometer Gravitational Wave Observatory, or LIGO, and Virgo. This has opened an entirely new field of astronomy, enabling us to measure the mass, spin, and distance of objects that are invisible to traditional telescopes. The existence of black holes provides a perfect laboratory for testing the extreme predictions of Albert Einstein's theory of relativity. They profoundly distort space and time, leading to observable effects like time dilation and gravitational lensing, where light from distant objects is bent around them. By studying their influence on nearby stars and gas, scientists can explore physics under conditions impossible to create on Earth. Supermassive black holes are critical actors in the story of how galaxies evolve. Their activity governs the rate of star birth, the arrangement of interstellar gas, and the overall dynamics of galactic structures. The energy unleashed during their feeding processes can propel gas clouds out of a galaxy, thereby suppressing new star formation, or fuel the brilliance of an active galactic nucleus. These interactions create a delicate balance between the growth of a galaxy and the influence of its central behemoth. The investigation of black holes is an ongoing effort that leverages telescopes operating across many wavelengths and employing various observational techniques. For instance, the Event Horizon Telescope, which functions as a radio telescope, was the first to successfully capture an image of a supermassive black hole's event horizon in the M87 galaxy. These kinds of observations give us a direct view of phenomena like the bending of light, the movement within the accretion disk, and the black hole's engagement with its cosmic neighborhood. From this, you can understand that black holes are not merely destructive forces. They also serve as catalysts for cosmic events. Their presence deeply influences the formation of galaxies, prompts the birth of new stars, and governs the flow of matter throughout space. This makes them unparalleled laboratories for exploring the most extreme conditions the universe has to offer, with each one holding clues to the fundamental laws of physics and the very fabric of the cosmos. When you think of a galaxy, picture a colossal system composed of billions of stars, vast clouds of gas and dust, and dark matter, all held together by the force of gravity. Galaxies exhibit a wide array of shapes, sizes, and stages of development, with each one possessing a distinct history of its creation, evolution, and interactions with its surroundings. We classify them into several primary types, such as elliptical galaxies, which are oval-shaped and dominated by old stars with very little star-forming gas. Then you have spiral galaxies, much like our own Milky Way, which feature prominent spiral arms that are vibrant hubs of new star formation. In contrast, irregular galaxies display no defined shape and are frequently the product of gravitational collisions and encounters with other galaxies. These vast star systems can also gather into groups and clusters, which in turn form even more massive cosmic structures. Our own local group, for example, contains the Milky Way, the Andromeda Galaxy, and dozens of smaller satellite galaxies. Clusters, on the other hand, can contain hundreds or even thousands of such systems. These immense congregations are bound by gravity and are in constant interaction, which affects everything from a galaxy's rate of rotation and its overall shape to its capacity for forming new stars. The structure of any given galaxy is ultimately defined by how its stars, gas, and dark matter are distributed. It's the dark matter, a substance that emits no light, but still exerts a powerful gravitational pull, that actually accounts for the majority of a galaxy's mass. The existence of dark matter is what explains the rotation curves we observe in spiral galaxies, where the outer regions spin much faster than their visible mass would suggest. The dynamics of galaxies involve a complex interplay of rotation, collisions, and mergers. When two galaxies collide, their gravitational forces compress vast clouds of gas, which can ignite a massive wave of star formation, create entirely new structures, and profoundly alter their shapes. In some cases, these encounters can cause spiral or irregular systems to transform into elliptical galaxies, while also distributing chemical elements across the galaxy and into intergalactic space. At the heart of most galaxies, you'll find massive central black holes that play a crucial part in their evolution. The energy unleashed as matter is pulled onto a black hole can propel gas clouds outward, effectively halting the formation of new stars and giving rise to what we call active galactic nuclei. These powerful processes create a delicate balance between the growth of a galaxy and the activity at its core. We study galaxies across the entire electromagnetic spectrum, from radio waves all the way to gamma rays, because each tells us something different. Radio telescopes map out cold gas and the structure of spiral arms. Infrared instruments peer through dust to reveal hidden star-forming regions. And X-ray observatories pinpoint active nuclei and the remnants of exploded stars, showing you that galaxies are constantly evolving systems. This evolution unfolds over billions of years, as smaller, younger galaxies gradually merge to form larger ones, creating new generations of stars and planetary systems along the way. As this happens, older stars conclude their lives as white dwarfs, neutron stars, or black holes, and the continuous interactions between galaxies redistribute matter and energy, weaving an incredibly rich and intricate cosmic tapestry. So, you see, galaxies are far more than simple collections of stars. They are the dynamic and interconnected systems that provide the foundational structure of our universe. By examining their classification, structure, and dynamics, we can piece together the processes of star formation, chemical enrichment, and cosmic interaction, ultimately revealing the long and complex history of the cosmos itself. Beyond individual galaxies, we find cosmic clusters, which are enormous assemblies containing hundreds or thousands of galaxies, all gravitationally bound into the large-scale structure of the universe. We categorize these formations into groups, clusters, and superclusters, based on the number and density of their galaxies and the amount of gas and dark matter they contain. A galaxy group is a smaller association, typically comprising up to a dozen large galaxies along with many smaller satellite systems. The local group, which includes our Milky Way and the Andromeda Galaxy, among roughly 50 smaller galaxies, is a prime example of such a formation. Within a group, constant interactions dictate the motion, collision, and merging of galaxies, which in turn drives star formation and the redistribution of gas. A galaxy cluster is a significantly more massive system, containing hundreds to thousands of galaxies, vast quantities of hot, X-ray emitting gas, and enormous amounts of dark matter. These clusters serve as the dense nodes within the cosmic web, connected by filaments of galaxies and gas. The largest of these structures are superclusters, which are composed of dozens or even hundreds of galaxy clusters and can stretch across hundreds of millions of light-years. By studying superclusters, astronomers like me can better understand the distribution of dark matter, the evolution of galaxies, and the dynamics of our expanding universe. You'll find that gravitational forces drive the mergers and collisions that reshape galaxies and ignite massive bursts of star formation. The intensely hot gas within galactic clusters exerts pressure on these galaxies, which in turn slows the movement of their internal gas and profoundly shapes the processes of star creation. Dark matter is indispensable to the formation and stability of these clusters. Its mass vastly outweighs that of all visible matter, creating the underlying gravitational framework that binds entire galaxies together. Without this invisible scaffolding, you wouldn't see galaxy clusters persisting for billions of years, and the universe's large-scale structure would be unrecognizably different. For astronomers, galaxy clusters function as enormous laboratories for investigating cosmic phenomena on the grandest scales. They allow us to observe gravity's influence on galactic motion, the birth of stars, and the distribution of chemical elements across vast distances. These clusters also act as crucial indicators of the universe's expansion rate, helping us measure the parameters of our cosmological model, including the density of dark energy and the total mass of all matter. To study these clusters, you should know that we rely on telescopes observing across the entire electromagnetic spectrum. X-ray observations unveil the hot gas and the intricate interactions between galaxies. Meanwhile, optical telescopes allow us to analyze the shapes and movements of stars, and radio telescopes are essential for detecting neutral hydrogen and magnetic fields, providing a complete picture of the cluster's structure, dynamics, and evolution. It becomes clear that cosmic clusters are far more than mere collections of galaxies. They are complex systems that constitute the very architecture of the universe. Studying them helps us grasp the interplay of matter, the crucial role of dark matter, the dynamics of cosmic expansion, and the evolutionary paths of galaxies, with each cluster serving as a living example of how gravity, matter, and energy create structures of infinite diversity and scale. Dark matter and dark energy represent two of the most profound cosmic mysteries, as they remain almost entirely invisible to direct observation, while exerting a tremendous influence on the universe's structure and evolution. Together, these two components make up more than 95% of the universe's total mass and energy, leaving the visible matter you see, stars, planets, and gas, as only a tiny fraction of the whole. Imagine dark matter as an unseen substance that makes its presence known only through its gravitational pull on everything we can see. It is the force that holds galaxies together, gives shape to galaxy clusters, and dictates the rotational speeds of spiral galaxies. All observations that visible mass alone cannot explain. In fact, without dark matter, the galaxies and vast cosmic structures you observe simply could not have formed as they did. Because dark matter does not interact with light or any other form of electromagnetic radiation, it is impossible for you to see it through a telescope. Instead, scientists must study it using indirect methods, such as analyzing the motion of galaxies, observing the gravitational lensing effect where dark matter bends light from distant objects, and examining its impact on the cosmic microwave background, the faint afterglow of the Big Bang. Our models suggest that dark matter is spread in enormous halos around galaxies, providing an invisible framework that guarantees their long-term stability. Dark energy is an even more perplexing phenomenon, a form of energy that is responsible for the accelerated expansion of the universe. We discovered its existence by observing distant Type 1a supernovae, which revealed that galaxies are not just moving apart, but are doing so at an ever-increasing velocity. Dark energy accounts for roughly 70% of the universe's total energy and actively works against gravity, pushing everything outward rather than pulling it together. You can see the combined effects of dark matter and dark energy on every cosmic scale. Within individual galaxies, dark matter anchors stars and gas, shaping spiral arms and preventing the galaxy from flying apart. On the grand scale of galaxy clusters, it forges the gravitational webs that bind galaxies, while dark energy drives the accelerated expansion of this cosmic web, influencing how matter is distributed throughout the universe. Modern cosmological frameworks, like the lambda cold dark matter model, or lambda CDM, treat dark matter and dark energy as fundamental components. You'll find that these models successfully explain the observed arrangement of galaxies, clusters, and cosmic filaments. And they also predict the universe's evolution from its infancy after the Big Bang to its current state. The predictions of these models align remarkably well with data from the cosmic microwave background, galaxy rotation curves, and observations of distant supernovae. Our investigation into dark matter and dark energy is an ongoing effort, utilizing a combination of powerful telescopes, satellites, and sophisticated laboratory experiments. Space missions, such as the James Webb Space Telescope, are mapping the distribution of dark matter and probing dark energy's influence on the universe's expansion. Back on Earth, particle detector experiments are actively searching for direct interactions between dark matter and atoms, which could finally reveal the secrets of its true nature. Dark matter and dark energy continue to stand as two of the greatest enigmas in modern science, challenging your most fundamental notions of the universe, space, and time. Though you cannot see them, and we have not yet observed them directly, their influence is woven into the very fabric of the cosmos, shaping every galaxy, cluster, and large-scale structure in existence. Unlocking the nature of dark matter and dark energy is therefore the key to understanding the fundamental laws that govern our universe. These invisible components ultimately dictate the course of cosmic evolution, the motion of galaxies, the distribution of all matter, and the acceleration of space itself. For us, they form the foundation of research that promises to revolutionize your entire understanding of reality. Streams of energy and particles known as cosmic radiation traverse the universe, providing us with vital information about its origins, structure, and ongoing evolution. By analyzing this radiation, astronomers are able to explore the most remote regions of the cosmos and comprehend processes that have played out over billions of years. The cosmic microwave background, or CMB, is the residual energy left over from the Big Bang. This nearly uniform microwave radiation, which has a temperature of approximately 2.7 Kelvin, permeates the entirety of space. The CMB features minute temperature variations that correspond to the primordial density fluctuations from which galaxies, clusters, and the vast structures of the cosmos eventually emerged. High-energy gamma radiation is produced under the most extreme conditions the universe has to offer. Its sources include supernova explosions, the accretion of matter onto black holes, the collision of neutron stars, and other cataclysmic phenomena. The study of gamma rays enables astronomers to pinpoint active galactic nuclei, pulsars, and similar high-energy objects, while also allowing them to validate models of elementary particles and matter interactions in extreme states. X-ray radiation is emitted from incredibly hot cosmic regions, where gas temperatures can soar to millions of degrees. The intense X-ray emissions from the hot gas in galaxy clusters, stellar coronas, and the remnants of supernovae are entirely invisible in the optical spectrum. Through X-ray observations, scientists can determine the temperature, density, and chemical makeup of these cosmic entities and uncover concealed active black holes and the remnants of massive stars. Cosmic rays are composed of high-energy particle streams, consisting mainly of protons and atomic nuclei that travel at velocities approaching the speed of light. These particles are propelled by supernova explosions, interactions between stellar winds, and active galaxies. As cosmic rays engage with magnetic fields and the interstellar medium, they generate secondary particles and gamma radiation, offering insights into particle acceleration mechanisms and the physical processes at work in extreme cosmic settings. The observation of cosmic radiation necessitates the use of highly specialized instruments. Satellites like the Cosmic Background Explorer, or COBE, the Wilkinson Microwave Anisotropy Probe, or WMAP, and Planck have meticulously mapped the cosmic microwave background, detailing its temperature fluctuations and the structure of the early universe. Meanwhile, telescopes such as Chandra and the X-ray Multi-Mirror Mission, or XMM Newton, detect X-ray emissions to reveal hot gas clouds and active galactic nuclei, and gamma-ray space telescopes like Fermi and Integral monitor high-energy processes and cataclysmic events. Analyzing cosmic radiation provides a direct window into the universe's distant past. The cosmic microwave background offers a snapshot of the cosmos just 380,000 years after the Big Bang. Observations in gamma and X-ray frequencies expose the activity of stars and galaxies across millions and billions of years, while cosmic rays supply data on particle acceleration and interstellar interactions. In essence, cosmic radiation functions as a series of messages from antiquity, delivering information about the universe's structure, composition, and dynamics. This allows scientists to construct models of cosmic evolution, verify theories on the formation of galaxies and clusters, probe the characteristics of dark matter and dark energy, and comprehend physics under the most extreme conditions. Each form of radiation unveils a distinct facet of the universe, collectively deepening our understanding of its fundamental nature and origins. Among the most enigmatic and extreme objects in the cosmos are black holes, which are regions of space with a gravitational pull so powerful that nothing, not even light, can escape. They arise from the collapse of massive stars, the merger of neutron stars, or the gradual accumulation of matter at the centers of galaxies, forming unseen gravitational wells that profoundly affect the movement of nearby matter and light. The mass of a black hole is intrinsically linked to how it was formed. Stellar black holes, born from the collapse of massive stars, possess masses that range from a few to several dozen times that of our Sun. At the centers of galaxies reside supermassive black holes, which can weigh anywhere from millions to tens of billions of solar masses. There also exist intermediate mass black holes, whose masses are in the hundreds or thousands of solar masses, but their origins and formation processes remain an area of active investigation. The immense gravitational force of a black hole defines a boundary known as the event horizon, a point of no return from which nothing can ever escape. Any object that crosses this threshold becomes an integral part of the black hole, with information about its prior state being preserved only through the black hole's mass, angular momentum, and electric charge. This concept is a cornerstone of astrophysics, deeply connected to Einstein's theory of relativity. An accretion disk is a rotating structure of gas and dust that orbits a black hole. As matter within this disk accelerates and experiences intense friction, it heats up to millions of degrees and emits powerful X-ray and gamma radiation. This phenomenon makes black holes indirectly detectable. While the object itself remains invisible, its significant influence on the surrounding space is revealed through brilliant displays of luminosity and energy. Relativistic jets are tightly focused streams of plasma that are ejected from the vicinity of black holes at nearly the speed of light. These jets are created by the complex interaction between powerful magnetic fields and the rotation of the accretion disk. They have the ability to stretch for thousands or even millions of light-years across space, impacting star formation, the distribution of gas in galaxies, and the dynamics of large-scale cosmic structures. Black holes also function as invaluable laboratories for the study of extreme physics. They provide scientists with a unique opportunity to test Einstein's theory of relativity in conditions of intense gravity, examine the behavior of matter under unimaginable pressures and temperatures, and explore the fundamental nature of space and time. Current research, including the observation of gravitational waves from merging black holes, is pioneering a new method for studying the universe through gravitational radiation. The collision of two black holes is a cataclysmic event where they merge into a single, more massive entity, unleashing a tremendous amount of energy as gravitational waves. The initial detection of these occurrences by the Laser Interferometer Gravitational Wave Observatory, or LIGO, and Virgo collaborations not only confirmed the existence of gravitational waves, but also heralded a new age in astrophysics. Analyzing these mergers provides researchers with invaluable data on the distribution, mass, and spin of black holes, as well as their effect on the surrounding cosmic material. The influence of black holes radiates far beyond the confines of their event horizons, as they actively regulate star-forming activity within galaxies and redistribute vast quantities of gas and dust. They are responsible for generating powerful jets and accretion disk structures, which in turn sculpt the dynamic movements of stars and clusters. At the heart of most galaxies, supermassive black holes serve a critical function in guiding galactic evolution and shaping the large-scale structure of the entire universe, making them fundamental elements of the cosmic ecosystem. Investigating these enigmatic objects helps unravel the deepest mysteries of gravity, space, time, and matter itself. This research deepens our comprehension of the fundamental mechanics that direct the development of galaxies, clusters, and the cosmos as a whole. Though invisible, these immensely powerful celestial bodies continue to fuel scientific curiosity and inspire profound awe. Formed from the core collapse of massive stars during a supernova explosion, neutron stars rank among the most dense and peculiar objects in the cosmos. A neutron star packs a mass comparable to our Sun's into a sphere only about 20 kilometers in diameter. This results in an object of almost unimaginable density, where just a single cubic centimeter of its matter would weigh hundreds of millions of tons. Neutron stars are composed almost entirely of neutrons, created when a star's core succumbs to its own immense gravity, forcing electrons and protons to combine. The resulting body possesses an exceptionally high density, an incredibly powerful magnetic field, and is typically in a state of rapid rotation. Despite their diminutive size, the gravitational pull of neutron stars is so potent that they profoundly warp space-time and alter the trajectories of any nearby objects. Certain neutron stars are observable as pulsars, which are celestial sources emitting periodic beams of radio waves, X-rays, or gamma radiation. This radiation streams from their magnetic poles, which are not aligned with their axis of rotation, producing a lighthouse-like effect as the beam sweeps past an observer's line of sight. Pulsars enable astronomers to precisely measure neutron star rotation speeds, analyze their magnetic fields, and even employ them as exceptionally accurate cosmic clocks. Among the most extreme varieties are millisecond pulsars, which are ultra-fast spinning neutron stars that can rotate thousands of times per second, typically formed in binary systems where they siphon material from a companion star. Another type, magnetars, possess magnetic fields millions of times more powerful than ordinary pulsars, and can erupt in brilliant flares of gamma and X-ray radiation. Both serve as unique laboratories for studying quantum and gravitational physics under conditions impossible to replicate on Earth. The birth of a neutron star occurs during a supernova, an event where a star's outer layers are blasted into space while its core implodes. This formation process is marked by intense radiation and particle acceleration, which creates vast expanding clouds of gas and dust known as supernova remnants. These remnants provide astronomers with a window into the life cycles of stars and the conditions of the early universe. A collision between two neutron stars is an exceptionally rare but tremendously energetic event, releasing powerful gravitational waves and short gamma-ray bursts. Such phenomena give scientists a chance to probe the properties of matter at extreme densities, verify physical laws in intense gravitational fields, and observe the cosmic synthesis of heavy elements like gold and platinum. The impact of neutron stars on their cosmic neighborhoods is substantial, as their intense magnetic fields and relativistic jets sculpt nearby gas clouds and influence the dynamics of star clusters. Furthermore, their mergers are a primary source for enriching the universe with heavy elements. These processes are therefore crucial components of the cosmic ecosystem, directly affecting the formation of new stars and the broader evolution of galaxies. Consequently, neutron stars are far more than just the remnants of stellar death. They are natural laboratories for extreme physics. They offer clues to the mysteries of gravity, magnetism, nuclear interactions, and the cosmic origins of the heaviest elements. Their study is essential for astronomers seeking to understand the fundamental laws of nature and the intricate processes that shape the universe from individual stars to entire galaxies. Supernovae represent the most powerful explosions in the cosmos, releasing more energy in a matter of minutes than our sun will produce over its entire lifespan. These violent events are fundamentally important to the evolution of galaxies, triggering the formation of new stars and seeding interstellar space with the heavy elements required for planets and, ultimately, life. These stellar explosions are broadly classified into two main types. The first kind happens when a massive star depletes its nuclear fuel, causing its core to collapse under its own gravity, and its outer layers to be violently ejected into space. The second type occurs in binary systems, where a white dwarf accretes matter from a companion star until it reaches a critical mass, igniting a runaway thermonuclear explosion. In either case, supernovae function as cosmic engines, driving the creation of new star systems across the universe. Material violently expelled from a star's explosion travels throughout the galaxy, where it compresses interstellar clouds and triggers the formation of new stars. In this way, every supernova provides the essential energy and raw materials for succeeding generations of stars and planets, fueling an unending cycle of cosmic creation and rebirth. Supernovae are also the universe's principal factories for heavy elements. During these immense explosions, materials like iron, gold, and platinum are forged and then scattered across the interstellar medium. If it weren't for these cataclysmic events, the cosmos would be devoid of the fundamental building blocks necessary for planets, their atmospheres, and life itself. Some supernovae are associated with gamma-ray bursts, which are incredibly potent emissions of high-energy radiation that you can detect from billions of light-years away. These bursts give scientists a powerful tool to investigate the birth of massive stars, the mechanics of core collapse, and how particles are accelerated in the most extreme environments imaginable. By observing gamma-ray bursts, astronomers can peer into the most remote and ancient occurrences in the universe, catching a glimpse of the era when the very first stars ignited. To properly observe supernovae, you need telescopes that operate across a wide range of spectral frequencies, from visible light to X-rays and gamma rays. Space-based observatories such as the Hubble and Chandra telescopes track fluctuations in brightness, examine spectral lines, and monitor relativistic jets. This information allows researchers to analyze the composition, temperature, and velocity of the ejected matter, which in turn helps them model the explosion, determine the original star's mass, and forecast the emergence of new star systems. Certain supernovae leave behind incredibly dense objects like neutron stars or black holes, which continue to exert influence on their cosmic neighborhoods. These supernova remnants can manifest as pulsars, form accretion disks, or launch powerful jets, and they often stimulate the birth of new stars in adjacent gas clouds. This entire sequence highlights the deep connection between destructive cosmic events and the life cycle of celestial bodies. Supernovae also function as indispensable instruments for gauging cosmic distances. Because Type 1a supernovae have a predictable peak luminosity, they are used as standard candles to calculate the distance to faraway galaxies and to map the expansion of the universe. It was through these precise observations that the accelerated expansion of the cosmos was discovered, revealing the presence of what we now call dark energy. Therefore, you can see that supernovae are far more than just brilliant cosmic spectacles. They are foundational components of cosmic evolution. They sculpt the formation of stars, disperse heavy elements throughout space, trigger the creation of new systems, and provide a unique laboratory for studying the laws of physics under the most intense conditions. Each supernova detonation is a moment of catastrophic change that drives the dynamics and progress of the entire universe. Nebulae are immense clouds of gas and dust that form some of the most breathtaking and enigmatic structures in the cosmos. They function as stellar nurseries where new solar systems are born, and as the scattered remains of stellar explosions, presenting you with a unique window into star formation and the evolution of galaxies. These cosmic clouds appear in a multitude of forms. Emission nebulae shine brightly as their gas is ionized by the ultraviolet light from young, hot stars, resulting in vivid and colorful formations. In contrast, dark nebulae don't radiate light but instead block it, creating striking silhouettes against the backdrop of distant star fields. Then there are planetary nebulae, which are the intricate and beautiful remnants of dying stars that have cast off their outer layers. The process of star formation inside a nebula is initiated by the gravitational collapse of a gas cloud. As the cloud contracts, dense cores develop and heat up until they trigger thermonuclear reactions, giving birth to new stars. This entire sequence can span millions of years and involves the ejection of excess material and the formation of protoplanetary disks, which eventually coalesce into planetary systems. Certain nebulae, including the Orion Nebula and the Lagoon Nebula, have been extensively studied because they are relatively close to Earth. Inside these cosmic nurseries, astronomers can observe the birth of stars with varying masses, track the motion of gas and dust, and analyze the interaction between young stars and their surroundings. These observations help you understand how solar systems are created and which processes shape the development of planets and the emergence of life. Nebulae also act as cosmic laboratories for analyzing the chemical makeup of the universe. They are composed of hydrogen, helium, and a rich assortment of heavier elements that were forged inside stars and later expelled into space. By analyzing a nebula's emission spectra, scientists can ascertain the concentration of different elements, determine the temperature and density of the gas, and measure the velocity of material within the cloud, helping to reconstruct the history of stars and galaxies. The appearance and structure of nebulae can be altered by external forces. Powerful stellar winds, intense ultraviolet radiation, and gravitational interactions all work to sculpt complex features like pillars, compressed globules, and vast, empty cavities. These dynamic interactions make nebulae not just visually captivating, but also active agents in cosmic transformation. Furthermore, nebulae are instrumental in distributing energy and matter throughout a galaxy. They serve as vast reservoirs of gas for future stellar generations, help regulate the rate of star formation, and interact with the remnants of supernovae to disperse elements across galactic distances. In this way, nebulae are essential to the cyclical nature of cosmic evolution, guaranteeing the perpetual renewal of stars and planetary systems. Finally, the phenomena unfolding within nebulae are a source of inspiration not just for scientists, but also for artists, photographers, and anyone who appreciates cosmic beauty. Their brilliant colors, extraordinary shapes, and dynamic activity create the impression of a living, ever-changing universe. Observing these objects allows you to grasp the sheer scale of the cosmos and the profound interconnectedness between the birth and death of stars, which ultimately defines the structure of every galaxy. I want you to think of nebulae as far more than just beautiful cosmic clouds. They are stellar nurseries, giving birth to new stars. They function as natural laboratories for studying the physics and chemical makeup of the cosmos, and they act as vast reservoirs of material for solar systems yet to be formed. When you examine these structures, you begin to grasp the intricate beauty of the universe and deepen your understanding of the processes that give it shape and vitality. Now, let's turn to galaxies. You should envision them as immense cosmic islands, vast systems composed of billions of stars, interstellar gas, dust, and dark matter, all gravitationally bound together. You will find that they come in an amazing assortment of shapes and structures, from elegant spirals and massive ellipticals to chaotic, irregular forms, each one telling you a unique story of its evolution and its interaction with the cosmic environment. When you observe spiral galaxies, such as our own Milky Way, you'll notice well-defined arms where concentrations of young, hot stars, gas clouds, and nebulae reside. The central area, which we call the bulge, is home to older stars and typically harbors a supermassive black hole. These spiral arms are formed by density waves that compress interstellar gas, thereby triggering star formation and creating a dynamic, vibrant space where new stars are continuously being born. Elliptical galaxies, by contrast, present you with a much simpler shape, ranging from nearly spherical to highly elongated, and they consist mainly of ancient stars. Because they contain very little gas or dust, the formation of new stars is an exceptionally rare event within them. You can often understand these galaxies as the product of cosmic mergers, where spiral galaxies have combined to create the massive, quiescent systems that dominate the centers of galaxy clusters. Then you have the irregular galaxies, which lack a symmetrical shape and are often the result of gravitational interactions or collisions with other galactic neighbors. These galaxies are loaded with large quantities of gas and dust, and are sites of very active star formation. For us astronomers, these objects provide a fascinating look into cosmic dynamics and the processes that redistribute matter and energy throughout the universe. If you zoom out even further, you see that galaxies cluster together into groups, forming the large-scale structure of the universe, which resembles a cosmic web of filaments separated by immense voids. In this grand design, dark matter plays an essential role, creating the gravitational framework that gathers galaxies and clusters along these filaments. By studying this large-scale structure, you help us understand how all matter is distributed across the cosmos and how galaxies have evolved over time. Galactic mergers are common throughout the universe, and these collisions lead to dramatic changes in galactic structure, the formation of new star clusters, and the redistribution of gas and dust. In some cases, a merger can awaken the central supermassive black hole, creating what you know as an active galactic nucleus, which emits relativistic jets and powerful radiation visible from millions of light-years away. These events allow us to study physics under the most extreme conditions. Studying galaxies also helps us understand the history of the universe itself. When you look at distant galaxies through telescopes like Hubble and the James Webb Space Telescope, you are effectively peering billions of years into the past, back to a time when the first stars and galaxies were forming. These observations provide you with invaluable insights into how cosmic structures developed and how matter was organized in the early cosmos. Galaxies also serve as the primary sources of chemical enrichment in the universe. The stars within them synthesize heavy elements, which are then dispersed throughout space during supernova explosions, providing the raw material for new generations of stars and planets. In this way, you can see each galaxy as a living ecosystem, where energy and matter are continually recycled, ensuring the ongoing development of cosmic systems. Moreover, the interaction of galaxies with their environment creates remarkable phenomena, like tidal tails, stellar streams, and clouds of hot gas. Observing these effects allows you to study gravitational influences, the dynamics of intergalactic gas, and the processes that trigger new star formation under extreme circumstances. You come to realize that galaxies are not just collections of stars, but key elements of cosmic structure, evolution, and dynamics that reveal the interconnectedness of our universe. Let's now consider black holes, which are objects with gravity so intense that nothing, not even light, can escape their grasp once it crosses their boundary. You'll find they are among the most mysterious and extreme phenomena in the cosmos, playing a critical role in the formation of galaxies, the acceleration of particles, and the redistribution of energy across space. They form in different ways, with stellar black holes emerging from the gravitational collapse of massive stars, while the supermassive black holes at the centers of galaxies grow to be millions or billions of times the mass of our Sun. The boundary of a black hole is marked by the event horizon, an imaginary surface that acts as a point of no return. Inside this horizon, the laws of physics as you and I know them no longer apply in familiar ways, and the density of matter approaches infinity, creating what we call a singularity. This makes black holes unique laboratories for you to explore the meeting point of extreme gravity and quantum mechanics. The space around black holes is often filled with accretion disks, rotating clouds of gas and dust that gradually spiral inward. As this material gets closer to the event horizon, it heats to millions of degrees, emitting powerful X-ray and gamma radiation that our space telescopes can detect. These observations allow you and I to determine a black hole's mass, its rate of rotation, and the structure of its accretion disk. In some cases, black holes can also launch relativistic jets, which are powerful streams of particles ejected at nearly the speed of light along their rotational axes. Stretching for millions of light years, these powerful jets propel energy and matter deep into the void of intergalactic space. Their presence profoundly shapes galactic evolution by governing the rate of star formation, influencing the arrangement of gas, and fostering intricate interactions with the cosmic environment. You find that some black holes are not solitary but exist in binary systems, closely orbiting a companion star. In these dynamic pairings, material from the star is drawn toward the black hole, which in turn unleashes brilliant X-ray emissions and causes periodic, energetic outbursts. Such binary systems present you with an extraordinary window into observing how matter behaves under the most extreme gravitational pressures, allowing for direct tests of general relativity. At the heart of most galaxies, including our own, lie supermassive black holes that are pivotal to the galaxy's entire structure and development. The activity of these central behemoths dictates the pace of star creation, the distribution of vast gas clouds, and the overall dynamics of their galactic homes, making them fundamental to our understanding of the universe's large-scale structure. By managing the movement of stars and gas within the galactic core, these black holes shape the formation of spiral arms, affect stellar density, and regulate the nucleus's activity. Observing them helps you and I grasp the vital cosmological relationship between the mass of a galaxy's core and its total mass. Beyond their structural role, black holes function as unparalleled natural laboratories for putting the laws of physics to the ultimate test. The recent breakthrough in detecting gravitational waves, produced by the collision of black holes, has launched a new age in astronomy, granting us the ability to witness cosmic events that were once completely hidden from view. Therefore, you should see black holes not merely as enigmatic and perilous objects, but as indispensable components of the cosmic architecture. They steer the course of galaxy formation, drive the redistribution of both matter and energy, and provide us with a means to probe the universe's most fundamental principles. Each of these objects offers a glimpse into an extreme cosmos, a realm where the laws of nature are revealed in their most awe-inspiring and dramatic forms. Gravitational waves are disturbances in the very fabric of space-time, generated by the acceleration of colossal objects like merging black holes or neutron stars. These ripples propagate at the speed of light, carrying with them information from the most distant regions of the universe, and offering astronomers and physicists an entirely new way to perceive reality. The concept of gravitational waves was first proposed by Albert Einstein within his general theory of relativity, where he outlined how massive accelerating bodies would create distortions in spacetime that spread much like waves on a pond. However, actually measuring these fluctuations turned out to be a monumental challenge, as even the most powerful waves produce incredibly slight deformations, distortions smaller than the width of a proton by the time they reach Earth. The very first direct observation of gravitational waves finally happened in 2015, achieved by the Laser Interferometer Gravitational Wave Observatory, or LIGO, in the United States. These facilities employ laser beams that are split and sent down long perpendicular tunnels, then reflected back to be recombined. A passing gravitational wave causes a minuscule change in the path lengths, which is then detected as a distinct interference pattern, a discovery that both validated Einstein's theory and inaugurated the field of gravitational wave astronomy. These cosmic ripples can be produced by a variety of events, but the most potent waves are unleashed by the merger of massive black holes or neutron stars. Such cataclysmic occurrences generate tremors in spacetime that can travel across billions of light years. Through these signals, you and other scientists can obtain direct knowledge about the mass, spin, and dynamics of objects that would otherwise remain unobservable. Unlike light, gravitational waves do not interact with matter, meaning they carry untainted information about events happening inside the universe's densest and most obscure regions. Thanks to an expanding network of detectors, including LIGO, Virgo in Europe, and CAGRA in Japan, astronomers can now pinpoint the location of these mergers in both space and time. By analyzing this data alongside electromagnetic observations from X-ray or gamma-ray telescopes, we can investigate not only the source's nature, but also its effect on the surrounding cosmic neighborhood. This new field also allows us to test the fundamental laws of physics by measuring the propagation speed of the waves and comparing it to the speed of light, which helps verify the precision of general relativity under the most intense conditions imaginable. Any detected variance could signal the existence of new physical phenomena, hint at additional dimensions, or reveal novel properties of dark matter and dark energy. While the influence of these waves on our planet is infinitesimally small, their detection has been nothing short of revolutionary, giving us a new sense with which to perceive the cosmos. You could say that we can now listen to the universe's rhythm, feeling its vibrations, and studying events that will forever remain invisible to conventional telescopes. In essence, gravitational waves represent more than just a scientific finding. They are a new instrument for comprehending the universe, enabling you to witness cataclysmic events, probe physical laws, and expand our knowledge of reality. This opens up unparalleled possibilities for future researchers as they continue to explore the cosmos. A different but equally fascinating area of study concerns exoplanets, which are worlds that orbit stars far beyond our own solar system. This research reveals new frontiers for astronomers, deepening your understanding of how planetary systems form, the incredible variety of worlds, and the specific conditions where life could potentially emerge. The journey began in 1992 with the first verified discovery of an exoplanet, when astronomers identified worlds orbiting stars much like our Sun. Now, thanks to space observatories such as Kepler and the Transiting Exoplanet Survey Satellite, or TESS, we have found thousands of exoplanets, ranging from scorching gas giants that hug their stars, to rocky planets situated in the habitable zone, where temperatures could permit liquid water to exist. Methods for finding exoplanets are remarkably diverse and clever. The transit method, for instance, involves detecting the faint dimming of a star's light as a planet passes in front of it from our point of view. Another technique, the radial velocity method, measures the tiny wobble of a star induced by the gravitational influence of an orbiting planet. In addition, methods like direct visual observation and microlensing enable us to identify planets at even more extreme distances, with each approach contributing to a more complete picture of distant planetary systems. Exoplanets themselves exhibit a tremendous amount of variation. You can find gas giants that resemble Jupiter and Saturn, super-Earths, which are more massive and dense planets with solid surfaces, and even frozen worlds encased in thick atmospheric layers. Some of these planets follow highly eccentric orbits that take them to the very edges of their systems, while others orbit perilously close to their host stars, experiencing temperatures that can climb to several thousand degrees Celsius. Of particular fascination are the planets located within the habitable zone, as these are worlds where conditions might be suitable for the presence of liquid water, and by extension, life. These planets are prime candidates for detailed investigation using spectroscopic methods. This technique allows us to analyze the chemical makeup of their atmospheres, searching for the presence of oxygen, methane, carbon dioxide, and other compounds that could hint at underlying biological processes. The search for life on these distant worlds stands as one of the ultimate objectives of modern astronomy. Scientists are on the lookout for biosignatures and chemical anomalies within planetary atmospheres, attempting to deduce where microorganisms or even more complex life forms could thrive. This line of inquiry involves modeling diverse climatic conditions, analyzing potential biochemical pathways, and drawing comparisons with the examples of life found here on Earth. Because exoplanets are so diverse, they allow us to envision alternative pathways for the evolution of planetary systems. Some worlds are defined by extreme climatic conditions, where oceans might be made of liquid methane or ammonia, and atmospheres are dense with hydrogen and helium. Other planets may have no atmosphere at all, leaving them vulnerable to the constant bombardment of cosmic rays and solar wind. This variety illustrates that the universe is far more rich and unpredictable than we could have possibly comprehended just a few decades ago. The study of exoplanets also provides profound insights into the history of our own solar system. When you compare the orbits, compositions, and masses of distant planets with those in our neighborhood, you can create more accurate models of planet formation and migration. This helps explain the causes behind their orbital resonances and the specifics of their interactions with the gas and dust disks present during the early phases of a system's development. Ultimately, exoplanets present a completely new lens through which you can view the universe. They showcase an astonishing diversity of worlds, offer a tangible chance to discover life beyond our own planet, and help us grasp the fundamental processes of how planets come to be. Every new world we find expands our cosmic horizons and motivates further exploration, transforming the act of observing the stars into a grand journey through the boundless realms beyond our own. Cosmic radiation is a continuous stream of particles and electromagnetic energy that comes from a multitude of sources throughout the universe. This phenomenon includes everything from the cosmic microwave background, a faint afterglow from the universe's earliest phase, to gamma rays and high-energy cosmic rays produced in stars, supernovae, and the cores of active galaxies. The cosmic microwave background, also known as the CMB, represents the oldest signal that you and I can observe. It emerged approximately 380,000 years after the Big Bang, at a time when the universe had cooled enough for electrons and protons to form neutral atoms, thereby allowing photons to travel freely. This ancient light holds invaluable information about the primordial structures of the cosmos, including fluctuations in temperature and matter density, which makes it a crucial tool for cosmological study. Gamma radiation consists of the highest energy photons in the electromagnetic spectrum. It is generated by cataclysmic events such as supernova explosions, the centers of active galaxies, particle collisions within relativistic jets, and the merging of compact objects like neutron stars. By studying gamma radiation with space telescopes like Fermi and Integral, astronomers can probe extreme physical processes that are otherwise impossible to observe in the visible or infrared spectrums, helping to map the most energetic events in the cosmos. Cosmic rays are composed of high-energy particles, predominantly protons and atomic nuclei, which travel at speeds approaching that of light. These particles can be ejected from the Sun, distant galaxies, supernovae, and even black holes. When they strike Earth's atmosphere, they trigger cascades of secondary particles that are then detected by sensors on the surface or in space. The study of cosmic rays helps us to unravel the origins of high-energy matter and the mechanisms that accelerate particles to such incredible speeds in the universe. This cosmic radiation has a significant impact on the space environment, influencing planetary magnetospheres and atmospheres. It contributes to the formation of the ionosphere, affects the chemical balance of the upper atmosphere, and poses a considerable risk to astronauts and spacecraft. By investigating the interaction between this radiation and the magnetic fields of Earth and other planets, you can develop better methods for predicting space weather and designing protective systems for long-term space missions. Furthermore, high-energy particles and gamma radiation act as natural laboratories for putting the fundamental laws of physics to the test. They create conditions far more extreme than anything we can replicate on Earth, offering a unique window into the workings of the universe at its most energetic levels. By analyzing the movement of cosmic rays, their behavior within magnetic fields, and any potential irregularities, we can uncover new particles, undiscovered forces, or unique characteristics of dark matter. This means that cosmic radiation is more than just a stream of energy. It's a profound source of knowledge about the universe's origins, its development, and its fundamental design. It provides us with a window into extreme cosmic events, allows us to verify the laws of physics, and opens up new frontiers in exploring the cosmos, enabling us to practically listen to and feel the universe's pulse across immense spans of space and time. Dark matter is an enigmatic substance that constitutes the majority of the universe's mass, yet it doesn't emit or interact with light. We infer its presence from the gravitational influence it exerts on visible matter, on cosmic radiation, and on the overall large-scale architecture of the universe. The concept of dark matter took shape in the 20th century, as astronomers observed that the speeds at which stars orbit within galaxies were inconsistent with the amount of visible mass from stars and gas. According to the principles of Newtonian mechanics, stars in the outer regions of a galaxy should orbit more slowly than those closer to the center. But they were found to maintain unexpectedly high velocities. This observation pointed to the existence of an unseen mass that was generating an extra gravitational force. This invisible substance, dark matter, is not only evident within individual galaxies, but also within vast clusters of galaxies. Through the study of gravitational lensing, a phenomenon where massive objects warp the light from more distant sources, scientists determined that the visible matter alone could not account for the observed distortions. This finding served as one of the most crucial pieces of evidence confirming the existence of dark matter, which remains invisible to our telescopes, but is clearly detectable through its gravitational effects. Several theories attempt to explain the nature of dark matter. One prominent idea suggests it is composed of weakly interacting massive particles, or WIMPs, which engage with ordinary matter solely through the force of gravity. Another possibility involves axions, which are even lighter hypothetical particles that could potentially form vast condensates and thereby shape the structure of the universe. There are many different approaches to searching for dark matter. In underground laboratories, Researchers are constructing detectors sensitive enough to capture the incredibly rare interactions between dark matter particles and ordinary matter. Meanwhile, astronomical observations in space look for anomalies in the distribution of galaxies, the motion of star systems, and radiation that could be produced by the collision of dark matter particles. In parallel, experiments at particle accelerators, such as the Large Hadron Collider, are aimed at creating these elusive particles in a controlled environment. Dark matter is fundamentally important to the formation of the universe's large-scale structure, acting as a gravitational scaffold upon which galaxies and their clusters are built. In its absence, the cosmos would be unrecognizably different, and galaxies might never have formed with the sizes and shapes that we see today. The interaction between dark and ordinary matter is so minimal that its detection presents an immense challenge. Nevertheless, its indirect consequences, such as gravitational lensing, the rotation curves of galaxies, and fluctuations in the cosmic microwave background, give astronomers the tools to map its distribution and investigate its properties. Consequently, dark matter stands as one of the most profound enigmas in modern science. Its existence challenges our conventional understanding of the universe, space, and time. And though it is unseen and not yet directly detected, its influence is felt in every corner of the cosmos, shaping galaxies, clusters, and the very fabric of existence. Unlocking the nature of dark matter is essential to deciphering the fundamental laws of our universe. Modern cosmological models also point to a relationship between dark matter and dark energy, the perplexing force that drives the accelerated expansion of the universe. A deeper understanding of dark matter's properties could illuminate the nature of this cosmic acceleration and resolve foundational questions about the composition of the cosmos. Dark matter is therefore an invisible yet crucial component that defines the structure of the universe, all while being governed by physical laws that remain a mystery to us. Its investigation paves the way for understanding the origins of galaxies, the dynamics of the cosmos, and the essence of matter itself, thereby creating new horizons for both astronomy and fundamental science. Dark energy is a baffling force that accounts for approximately 70% of the total energy in the universe and is the cause of its accelerating expansion. While its true nature is still unknown, exploring dark energy is crucial for comprehending the ultimate fate of the universe and its underlying principles. The discovery that the universe's expansion is speeding up was made in the latter part of the 20th century. Astronomers, while observing distant Type 1a supernovae, realized these cosmic markers were moving away from us faster than predicted by models of a decelerating expansion. These observations led to the startling conclusion that space is not merely expanding, but is doing so at an ever-increasing rate, which implies the presence of an unknown form of energy that counteracts gravity. Several hypotheses have been proposed to explain the nature of dark energy. The most recognized of these is the cosmological constant, a concept originally introduced by Einstein into his equations of general relativity, which describes the energy inherent to the vacuum of space, distributed evenly everywhere. Alternative theories propose the existence of dynamic fields, referred to as quintessence, which can change over time and thus have a variable impact on the rate of cosmic expansion. Dark energy has a profound effect on the large-scale structure of the universe, dictating the speed at which galaxy clusters drift apart and influencing the formation of new galaxies. If this force were not present, the accelerated expansion would not be happening, and the universe's evolution would have followed a completely different path, perhaps leading to a much higher concentration of matter in its earlier phases. To investigate dark energy, scientists rely on several key observations, including supernovae, the cosmic microwave background, the large-scale distribution of galaxies and their clusters, and the phenomenon of weak gravitational lensing. These approaches allow us to precisely gauge the universe's expansion rate and gather insights into how energy is arranged across space and time. Advanced observatories like the Hubble Space Telescope, along with upcoming missions such as Euclid and WFIRST, are designed to collect crucial data that will help us narrow down the properties of dark matter and dark energy, clarifying their overall influence on the cosmos. One of the most profound puzzles surrounding dark energy is its interaction with gravity and ordinary matter. It only becomes apparent across immense cosmic distances, making it undetectable within localized environments like our own solar system. This characteristic makes dark energy exceptionally difficult to investigate. Yet it also presents a fascinating challenge for physicists who aim to integrate it with the other fundamental forces that govern the universe. Dark energy and dark matter collectively establish the foundational structure of our universe. While dark matter acts as a cosmic glue, holding galaxies together and fostering the formation of cosmic structures, dark energy exerts an opposing force, driving these structures apart and accelerating the expansion of space. The interplay between these two forces ultimately governs the dynamics of the cosmos and shapes its evolution over billions of years. By understanding the nature of dark energy, we open up the possibility of forecasting the ultimate destiny of the universe. Depending on its specific characteristics, the cosmos might continue its accelerated expansion, leading to a future where it becomes progressively colder and more desolate. However, more intricate scenarios are also conceivable, involving shifts in cosmic dynamics that could lead to periods of deceleration or other transitional phases. Therefore, dark energy stands as one of the foremost enigmas in modern cosmology, offering a key not only to the universe's accelerated expansion, but also to the fundamental laws of nature and the fate of all galaxies. Black holes are defined as regions in space-time where the gravitational force is so overwhelming that nothing, not even light, can break free from their grasp. They typically originate from the remnants of massive stars at the conclusion of their life cycles, but can also emerge from the collision of compact objects or through the steady accumulation of matter at the hearts of galaxies. The formation process is initiated when a giant star depletes its nuclear fuel, causing its core to collapse under its own immense gravity. If this core's mass surpasses a critical threshold, the collapse is unstoppable, culminating in a singularity, a point of infinite density, shielded by an event horizon, the boundary beyond which we can observe nothing. We classify black holes based on their mass into three main categories: stellar, intermediate, and supermassive. Stellar black holes, possessing masses several times that of our Sun, are born from the collapse of a single star. Intermediate mass black holes can have masses equivalent to hundreds or thousands of suns, whereas supermassive black holes, found at the centers of most large galaxies, can weigh millions or even billions of solar masses and dominate the dynamics of their galactic cores. Surrounding a black hole is a swirling vortex of matter known as an accretion disk, where material spirals inward before being consumed by the singularity. This process unleashes tremendous quantities of energy, visible to us as powerful X-ray and gamma-ray emissions, which scientists can detect using both Earth-based and spaceborne telescopes. Through these observations, we can not only locate black holes, but also examine the behavior of physics under the most extreme gravitational pressures imaginable. Among the most energetic events in the cosmos is the merger of two black holes, a cataclysmic collision that generates gravitational waves, ripples that distort space-time and travel across vast cosmic distances. Specialized detectors like the Laser Interferometer Gravitational Wave Observatory, or LIGO, and Virgo are capable of recording these waves, ushering in a revolutionary new chapter in astrophysics. This capability allows us to directly study the properties of black holes, including their mass, spin, and the intricate dynamics of their mergers. Black holes exert a profound influence on their surroundings, extending far beyond their event horizons. They can launch powerful jets and streams of particles, heat vast clouds of interstellar gas, and play a crucial role in regulating the pace of star formation within the nuclei of galaxies. For instance, the supermassive black hole at the center of our own Milky Way galaxy directs the motion of millions of stars and vast quantities of cosmic dust, orchestrating the complex structure around it. A compelling theory also proposes that some black holes could be primordial objects, relics from the earliest moments of the universe following the Big Bang. The existence of these ancient black holes could potentially account for a portion of the universe's mysterious dark matter, and may have influenced the formation of the very first galaxies. Furthermore, the phenomenon of Hawking radiation suggests that black holes are not perfectly black after all. Due to quantum effects near the event horizon, a black hole can slowly lose mass and, over immense timescales, eventually evaporate, uniting the principles of gravity, quantum mechanics, and thermodynamics. Ultimately, black holes are far more than mere agents of cosmic destruction. They are complex systems that actively shape cosmic dynamics, radiate vast amounts of energy, and offer a unique window into the fundamental laws of nature. They continue to be a source of profound mystery and inspiration, enabling us to explore physical conditions that are impossible to replicate on Earth, and to delve deeper into the secrets of the universe's origin and evolution. Neutron stars represent the astonishingly dense cores left behind by massive stars that have exploded as supernovae. While their mass is comparable to that of our Sun, it is compressed into a sphere no larger than a few tens of kilometers across. This incredible compression results in extreme physical conditions that cannot be found anywhere else in the universe. The creation of a neutron star is triggered by the gravitational collapse of a star's core during a supernova. This collapse is halted by the immense pressure of degenerate neutron gas, a state of matter where protons and electrons have been forced together to form neutrons. The outcome is an object of almost pure neutron matter with a density rivaling that of an atomic nucleus. Certain neutron stars are observable from Earth as pulsars, which are objects that emit focused beams of electromagnetic radiation with remarkable precision. These pulsars are characterized by their incredibly rapid rotation, capable of completing hundreds or even thousands of revolutions every single second. As these beams sweep across space, we detect them as regular pulses, making pulsars some of the most reliable cosmic clocks known to us. When the radiation beams from pulsars sweep across our planet, you see astronomers detect them as periodic flashes, much like a lighthouse in the cosmos. By studying these pulsars, we gain the ability to probe the fundamental laws of physics as they operate under the most extreme conditions imaginable, offering insights that are otherwise inaccessible to us. These objects possess incredibly powerful magnetic fields, billions of times more intense than that of Earth, which in turn generate extraordinary effects. One such effect is the acceleration of particles to relativistic velocities, approaching the speed of light. This makes pulsars invaluable for testing the theory of relativity, examining the properties of dense neutron matter, and refining our models of the internal composition of these compact stars. Neutron stars are also key players in some of the most dramatic cosmic spectacles, such as their mergers with other neutron stars or black holes. These cataclysmic collisions produce gravitational waves, which are detected by facilities like LIGO and Virgo. Furthermore, these events eject heavy elements, including gold and platinum, into the interstellar medium, a process that is absolutely essential for the chemical evolution of galaxies. Among neutron stars, you can also find some truly unusual varieties. For instance, magnetars have magnetic fields so immensely powerful they hold the record, capable of ripping apart atomic nuclei and unleashing gamma-ray bursts of staggering energy. These unique objects function as natural laboratories, allowing us to investigate how matter behaves in extreme magnetic fields, and helping us grasp fundamental physical processes that cannot be replicated in any laboratory on Earth. To observe neutron stars, we rely on a combination of radio telescopes, along with X-ray and gamma-ray observatories. These instruments allow us to meticulously record their rotation, measure subtle shifts in their pulse frequency, and ascertain the characteristics of the matter they emit. This wealth of data is crucial for constructing precise models of neutron star structure, their evolutionary paths, and the dynamics of their interactions with the surrounding cosmic environment. Neutron stars also play a vital role in the formation of binary systems and the creation of powerful X-ray sources. In these systems, material from a companion star can be pulled onto the neutron star, forming a scorching accretion disk that radiates intensely in the X-ray spectrum. This powerful X-ray emission is something astronomers can then detect across vast cosmic distances, giving us another window into their behavior. Ultimately, you can see that neutron stars and pulsars are truly astonishing celestial bodies that push the boundaries of known physical laws. Their study helps us comprehend the structure and evolution of matter under conditions of extreme density, magnetic force, and gravitational pull, consistently opening up new frontiers in our exploration of the universe. Supernovae represent the magnificent explosions of massive stars, signaling the end of their life cycles and leaving behind either a neutron star or a black hole. These events unleash a phenomenal amount of energy, capable of briefly outshining an entire galaxy, and they stand as the universe's principal source of heavy elements. Depending on the mechanism of the explosion, you'll find that supernovae are categorized into several types. A Type 1a supernova, for example, results from the collapse of a white dwarf in a binary system, after it has siphoned off a critical amount of mass from its partner star. In contrast, a Type 2 supernova takes place when a massive star undergoes gravitational collapse after it has completely depleted its nuclear fuel, with each type producing distinct spectral lines and energy signatures that astronomers can record. The process of the explosion itself involves a swift contraction of the star's core, which is immediately followed by the violent ejection of its outer layers into the surrounding space. So much energy is liberated in this event that for a period of several weeks or even months, a single supernova can appear brighter than all the other stars in its galaxy combined. This provides a critical opportunity for us to study stellar physics, the properties of the explosion, and the complex mechanisms of element synthesis. Supernovae are effectively the primary cosmic factories for heavy elements such as iron, gold, silver, and platinum. Inside the fiery crucible of the explosion, extreme temperatures and pressures foster the conditions necessary for nucleosynthesis, a process we cannot replicate in any lab on Earth. These newly forged elements are then scattered throughout the galaxy, becoming the building blocks for new stars, planets, and even life itself. Observing supernovae also provides a method for measuring the expansion rate of the universe. Because Type 1a supernovae are so bright and have a standardized luminosity, they function as cosmic beacons, allowing astronomers to calculate distances to faraway galaxies. It was precisely these kinds of observations that led to the discovery of the universe's accelerated expansion and gave rise to the hypothesis of dark energy. Additionally, supernovae give rise to remnant nebulae, which become fertile grounds for the formation of new stars. The ejected material's interaction with the interstellar environment forges complex structures, including shock waves and vast clouds of gas and dust. These dynamic processes actively regulate the pace of star formation and the overall evolution of galaxies, thereby influencing their shape and chemical makeup. When we are fortunate enough to observe supernovae in nearby galaxies, it presents a particularly valuable opportunity because we can study the intricate details of the explosion with exceptional precision. Observatories that detect X-rays and gamma rays can capture the rapid bursts of energy, while optical telescopes track the expanding shells of debris. This comprehensive data helps us model the explosion's dynamics, its energy distribution, and the elemental composition of the ejected material. Supernovae can also propel relativistic jets of particles into space, which contribute to the cosmic rays that eventually reach Earth and interact with our magnetosphere. By studying these phenomena, you help us understand the processes behind particle acceleration and their profound impact on the interstellar medium. Therefore, you should see that supernovae are far more than just beautiful cosmic fireworks. They are a linchpin of the cosmic ecosystem, responsible for synthesizing heavy elements, creating the remnants from which new stars are born, and playing an indispensable role in the evolution of galaxies. Investigating them reveals the fundamental processes that govern the life and death of stars, and by extension, the fate of entire galaxies. Cosmic radiation is a continuous stream of high-energy particles that permeates all of space, with origins both within our solar system and from distant galaxies. It is composed mainly of protons, helium nuclei, and other heavy elements traveling at relativistic speeds, along with high-energy electromagnetic radiation. This cosmic radiation comes from a variety of sources. Here in our solar system, the Sun is the main contributor, emitting solar winds and flares that are filled with charged particles. Looking beyond our solar system, however, you find that the primary sources are much more energetic events and objects, including supernovae, neutron stars, pulsars, and the active nuclei of other galaxies. When cosmic radiation travels through the interstellar and interplanetary medium, it interacts with matter, generating secondary particles, gamma rays, and neutrinos. You'll find that these interactions provide us with invaluable data, allowing us to probe high-energy physics, construct models of galactic magnetic fields, and gain a deeper understanding of the events unfolding in the cores of active galaxies. To capture this information, we use an array of detectors, both in orbit and here on Earth's surface. These instruments are designed to register the particles and energy arriving from deep space, which enables us to trace them back to their potential sources and map their distribution across the celestial sphere. The effect of cosmic radiation on any given planet is largely determined by its atmosphere and magnetic field. For instance, you and I are shielded from the majority of high-energy particles by Earth's robust magnetosphere and dense atmosphere, which effectively absorb and deflect this incoming energy. However, for a world like Mars, which lacks a significant magnetic shield, cosmic rays have a much more direct impact on the surface, presenting serious challenges for the potential existence of life and for any future human missions we plan. Here in Earth's upper atmosphere, cosmic radiation is responsible for some fascinating phenomena, such as the creation of radionuclides like carbon-14 and the ionization of gases that influence our weather and electrical processes. You should also know that this same radiation can disrupt the electronics on our satellites and poses a significant health risk to astronauts, compelling us to engineer advanced shielding and protective systems for space travel. When we observe cosmic radiation, we rely on highly specialized instruments, like scintillation and Cherenkov detectors, which are positioned both on the ground and aboard spacecraft. These devices allow us to measure the energy, trajectory, and composition of incoming particles, helping us identify spikes in activity and trace radiation bursts back to solar flares or cataclysmic events far across the cosmos. I find the cosmic rays with extremely high energies to be particularly captivating, as their origin is still something of a mystery. These particles can possess energies far beyond what we can achieve in our most powerful artificial accelerators, essentially turning them into natural laboratories for exploring elementary particle physics under the most extreme conditions imaginable. Current hypotheses suggest they might originate from the hearts of active galaxies or from violent mergers between black holes and neutron stars. Ultimately, you can see that cosmic radiation is a fundamental force in the evolution of planets and stellar systems, shaping chemical compositions and driving the formation of gas clouds and new stars. It also gives us a crucial method for testing our models of galactic magnetic fields and high-energy physics, investigating how heavy elements are created, and evaluating the inherent risks of interplanetary voyages. So, I want you to think of cosmic radiation not merely as an invisible flow of particles, but as a powerful diagnostic tool for exploring the universe. It helps us uncover the fundamental physical laws that dictate the structure of galaxies, the life cycles of stars, and the evolution of planets, beautifully connecting the micro-world of particles with the grand scale of the cosmos. When we turn our attention to the future of the universe, it's a subject that merges our latest scientific findings with profound hypotheses about cosmic evolution over billions and even trillions of years. To understand what lies ahead, you have to realize we rely on observations of the current expansion of space, the movement of galaxies, and the behavior of stars, all interpreted through the lens of high-energy physics. Our current data confirms that the universe is not only expanding, but that this expansion is actually accelerating, driven by a mysterious force we call dark energy. While gravity successfully binds together individual galaxies and clusters, the ever-increasing distances between these structures mean that, in the far future, galaxies will recede from one another until they eventually vanish from our observable horizon. On the scale of individual stars and galaxies, you can anticipate some truly complex evolutionary paths. Stars will progressively burn through their nuclear fuel, transforming into white dwarfs, neutron stars, or black holes. As interstellar gas clouds are used up, the birth of new stars will slow dramatically until eventually Some galaxies will become almost entirely devoid of the raw materials needed for star and planet formation. As billions of years pass, the gravitational dance of galaxies and the merging of massive clusters could result in the creation of enormous galactic superstructures. Some of our models predict that in this distant epoch, after the last stars have burned out, you would find only the cold and darkness of space, populated by the quiet remnants of white dwarfs, neutron stars, and black holes slowly radiating their energy away. Black holes in particular play a central role in this long-term forecast for the universe. They will continue to consume matter and merge, growing into ever more massive objects. Yet, according to Stephen Hawking's theory, even these cosmic giants are not eternal. They are predicted to gradually evaporate through a process known as Hawking radiation, which slowly converts their mass back into low-energy particles and photons until they, too, may vanish completely. Throughout this cosmic evolution, the fundamental laws of physics will continue to govern the universe, including the processes of elementary particle synthesis and decay. While matter and energy will undergo transformations on immense timescales, new structures and events may still form, though you would find their intensity and scale to be greatly diminished over time. This brings us to a rather philosophical perspective on the universe's destiny, where we must grapple with the idea of infinite expansion alongside the finite activity of matter. The image that emerges is one of an increasingly dilute, cold, and dark cosmos, a state of cosmic emptiness where the vibrant processes of life and celestial activity as we know them gradually fade into silence. What lies ahead is not an end in the conventional sense, but rather a profound cosmic transformation into a new epoch. In this future state, novel varieties of energy and matter could potentially emerge, even if they are confined to exceptionally sparse and secluded pockets of space-time. Investigating the universe's ultimate destiny helps us grasp the immense scale of cosmic phenomena and provides vital clues for understanding the basic principles of physics. By analyzing data from supernovae, gravitational waves, galactic distribution, and dark matter, scientists can construct models that forecast the cosmos's evolution for billions of years, creating theories about its eventual structure and behavior. In essence, the universe's future can be seen as an intricate dance of time, matter, and energy, playing out across boundless cosmic distances. This progression encompasses the entire life cycle of the cosmos, from the formation and death of stars and the collision of galaxies to the eventual cooling of black holes, all leading toward a state of profound stillness and infrequent activity. Even in this state, the cosmos remains an element within an unending cycle of being, continually raising timeless inquiries for both scientists and philosophers about the fundamental nature and ultimate destiny of everything that exists.